All right, I think it's about time to start. Can you all hear me? Perfect. All right, then I'm glad to say that we are arrived to the third and final session of this workshop. And the speakers of these sessions will be Dr. Al Rizzi from Boston Dynamics, Professor Janet Bogg from Stanford University, and Professor Astrid Drake from Toyota Research Institute and MIT. The first speaker of this session is Dr. Al Rizzi, and Dr. Al Rizzi is currently the chief scientist at Boston Dynamics, where he directs research and product developments for Spot robot. And today he's going to give a talk on supervised local autonomy for mobile manipulations with Spot. With this, Al, the stage is yours. I put you as presenter, and now you should be able to share your screen and start whenever you want.
Yep, just got to push the right buttons here.
Great. Yep.
Hopefully that looks good for everybody.
I think so.
Outstanding. Well, it's a pleasure to be here this evening, afternoon, whatever time it is in your time zone. So yeah, I am the chief scientist at Boston Dynamics, and I'm going to talk about the way we have been looking at developing mobile manipulation on Spot. And I think, at the core, we really see this as a way to deliver the hands, the part of a complete system that's going to actually touch the world. And what I'm going to talk about is our approach to building a set of low-level capabilities and functions that we think are really going to enable that. But since I work at Boston Dynamics, I have to start with a proper video. And hopefully you guys all get audio for this. So this is a set of Spot robots performing a bit of choreographed dance that we put together as part of our announcement for closing our deal with Hyundai. And just, a few behind the scene notes. There are, in most of these sequences, there are either 5 or 7 robots, most with arms. They're doing choreographed dance, but they're not really coordinating with one another, right? They're all watching a wall clock and playing out a prescribed dance sequence against a wall clock. I think the thing that's, remarkable about this is, of course, the agility of the machines and the fact that we can actually put something like this together over the course of about a week or two's worth of effort. And most of that effort wasn't actually engineering effort. Most of that effort was actually choreography and some art associated with how do you actually make this these robots be expressive and communicate something. All right, so mobile manipulation, back to the real world. We really want to enable the robots in general, and Spot in particular, to reach out and touch and interact with the world. We think that the way to do that is really through what we would describe as supervised local autonomy. Sometimes we use the phrase athletic intelligence. It's really similar to how we make mobility, for the most part, just work on the robot. And if you've ever used or seen one of our robots in a demo, you'll realize that, the robot takes care of a lot of the low-level details associated with how it gets around in the world. It's constantly choosing where to place its feet, how to maintain balance, all of the details that make locomotion relatively difficult. You as an operator simply tell the robot, hey, go in that general direction, go about this fast. Sometimes you pass hints to it. We have a hint that we like our users to pass to the robot whenever it's going to go climb up or down a flight of stairs. And it doesn't really matter whether it's explicitly a user who's passing that hint or some other, what we would call client-side control system or AI system that's driving the robot. And really what we're trying to do is very similar things for manipulation. So our initial focus is really on what we would call supervised teleoperation and an API that supports that. We're really trying to support low bandwidth manual remote operation of the robot. We're trying to support experimentation by both researchers and industrial users who are looking for how they might take advantage of mobile manipulation on a legged platform. And we're building an API that allows third parties to build applications around all of those capabilities. So the arm itself is really fully integrated with the base robot. It's a 6-degree of freedom arm with a relatively simple clamshell gripper on the end of it. The arm weighs about 8 kilos, has a total length of a little bit over a meter. Endpoint velocity is about 10 meters per second, about 5 kilos of continuous lift at half extension for the arm. The gripper will generate about 130 newtons of clamp force at its fingertips. We have a few sensors that are integrated into the gripper. Those include a relatively high resolution RGB camera, as well as a depth sensor, a time of flight, imaging sensor. And then we have an add-on port in the gripper to allow, again, third parties, users to put custom sensors and things like that out at the end effector. So we can deliver about 50 watts of power. We bring our Ethernet network that runs inside the robot out there, as well as a timing signal. What I'm really going to talk about today are the behaviors that we're paying attention to and trying to deliver along with this. So there's integrated behaviors for grasping, semi-autonomous object manipulation. So this is for doing things like turning valves, opening, closing valves, turning switches, flipping levers. You may have seen videos of us opening doors. We're delivering that as integrated behavior on the robot. We have an integrated tablet UI that gives a user or developer access to all of these functions, but all of those functions that we expose over that UI are also available over an API that we make available to anybody who's using the robot to really, again, encourage them to develop their own off-board autonomy systems, planning systems, and higher level applications. So there's nothing that you're going to see us do through the tablet and the UI that isn't already accessible. So let's watch a video of the robot doing, what we think of as, a day in the life kind of scene. So the robot opens a door, walks through the door, goes over to this electrical box. The user says, "Hey, I want to grasp." So they orient the robot so it can see the thing they want to grasp. They make a tap on a tablet to get the robot to grasp the handle. They say, "Hey, I want to turn that switch knob." Again, relatively simple interaction. They can tell the robot to actually flip the switch on, turn on the lights. We'll then switch to using some off-robot compute to do a trash cleaning task. So here there's an off-robot classification system that's been trained to recognize, junk on the floor. That's actually driving the robot to cause it to pick that object up and deposit it back in the bucket. Once that's done, user takes over control again. We see the dripping green goo coming out of the pipe. You can actually go ahead and use the camera in the gripper to go inspect that. And then walk the robot over to this quarter turn ball valve. And again, using the same grasping primitives, this time using a slightly different version of that tooling. We go tap on the place we want to grasp. In this version, the user is presented with an opportunity to basically specify a bunch of grasp constraints. Once they actually get them specified, they can either manually or automatically go ahead and have the robot execute that grasp. And again, we use this constraint manipulation to go turn the valve and, stop the leak, save the world, make everything great for humanity, because, hey, that's what robots are supposed to do. All right, so what I really want to do is I want to go through that video in careful detail and talk about each of the behaviors that you saw in it and talk about how we do them. The very most basic thing you saw there was this supervised grasping capability. And this really allows the client to specify grasp constraints. So you saw us take advantage of some imagery coming off of the camera, as well as a few renderings of the pose of the robot, to allow a user to fully specify exactly how they wanted to grasp an object. In parallel with that, we have fully automated grasping, where we actually run a grasp planning system on robot. And that goes ahead and both plans and executes grasp based on depth image data coming from that sensor. Well, comes from the sensors on the robot that it uses for locomotion, as well as the sensor in the gripper. So it actually performs it is a visually servoed grasping action to go grab the object, and it'll pick what it thinks is the best geometry for grasping what it sees on the floor or wherever it is. You also saw the automated door opening behavior. Again, there are some hints that we need from our client or user. Basically, they have to tell us, hey, the handle is about here and the hinge of this door is, on your left or on your right. We then go use basically a modified version of that grasping system to use, again, the depth data to actually localize the door handle and plan a grasp for it. And there are both automated as well as what we call warm start versions of the door opening behavior. The automated one, you specify that little bit of information, the robot will open the door and proceed to walk through. In the warm start version, in particular for more geometrically difficult doors or handles, will allow the user to either manually or use our other automation tools to grasp the handle and then hand over control to the robot. And this is all integrated with the base locomotion and obstacle avoidance capabilities that are built into the robot. We have a dragging feature that allows the robot to basically play tractor and grab onto something significantly heavier than it could lift and pull it across the floor. You saw some of the constrained manipulation capabilities, and this is really about interacting with the environment and the constraints that exist in the environment. So turning valves, turning cranks, flipping switches, all of those things that require sort of force-mediated and force-controlled interaction. And then one of the core functionalities we have is something we refer to as drive the hand, which really allows you to drive the entire robot as well as the arm by simply flying the hand through the world. And this is, very useful for both performing inspection tasks like you saw when we were closing the leaky valve and for gross positioning of the arm. So let's go through these in a little bit more detail. The first thing I talked about are these supervised grasping capabilities. And as I said, there are basically two types of this. There's the fully automated pick up an object functionality. So the user does image-based target specification. I should really say client, right? Because I don't care whether it's a user or some higher level planning decision-making system. But quite simply, they click on an image location or pass to us an image location out of the cameras off of the robot. The on-robot autonomy really takes over and fully executes a grasp. So it looks at depth imagery coming out of the on-robot cameras, depth imagery that we get off of the gripper camera, and then we'll actually servo the arm to successfully make a grasp on that type of object. Very low overhead for the client system, gives you, relatively quick grasping of reasonably standard objects. Doesn't guarantee a particular grasp pose. We also have what we refer to as the grasping wizard, which really lets the user or client explicitly specify the grasp they want to execute. They can constrain up to all 6 degrees of freedom of the grasp before it actually, the robot closes the gripper. And this is relatively useful for getting specific grasps on things like valves and switches, where, you as the user or the higher level system knows something about, risks of collision and the like with regard to particular grasps. And again, both of these modes are fully supported, both through the tablet AI as well as, or tablet UI, I'm sorry, as well as through the API. So here's just a demonstration of the robot picking up a bunch of random objects in one of our engineers' yards during COVID times. So, tap on the object, say, I don't care what orientation you grab it from. it'll go grab this stick. The robot has never, been trained or explicitly programmed to pick up and carry sticks. But hey, we can tidy up the yard. We can also pick up, trash off of the driveway. So obviously a slightly simpler situation to, successfully pick up the water bottle. We can pick up the random pipe fitting and shoes that you may leave lying around. And again, you see the robot sort of making decisions about what the best way to grasp these objects are. For that particular fitting, right, it chose to grab the flange. For the shoes, it'll, tend to grab them across the toe box. And, I think the point here is making these low-level capabilities as reliable as possible in order to really make it viable to automatically interact with a large number of objects in a reliable way, and to essentially alleviate the burden of needing to explicitly plan, detailed kinematics and motions in order to accomplish these kinds of tasks. Same thing for the grasping wizard. This obviously gives us much more control over the specific geometry of the interaction. So again, you tap on the image, the robot, looks at the depth data it has, goes and figures out how to point the in-hand camera at that target. You can then control the orientation of the gripper with respect to that target, essentially specifying an approach angle. I'm going to play that again because it goes kind of fast. So you can specify an approach angle, and then once that's specified, we present a little bit of information about the measured depth to target. So once we get the gripper lined up and say, yeah, go ahead, you see this vertical image that includes a white mark, which is where the robot has measured the target object to be at. And if you choose to automatically grasp it, the robot will just close on that and secure the gripper around it. You can also perform that step manually. And by manually, really what it means is you can pass velocity commands to the robot saying, please go close at this rate. And then once you're happy, you can tell it to stop closing and secure the grasp. Door opening, obviously we have this fully automated mode where what you do is, again, visually touch on the door handle. The robot will go and approach that, actually use the gripper to acquire relatively accurate depth data, and then go ahead and grasp the door handle, open the door. Of course, we are very interested in making sure we can open sprung doors, so it'll put its foot in the door to block it. Once it's got its foot in the door, it'll reach around and recirculate the arm to grab the far side of the door so it can open it all the way, and then go ahead and walk through. We can also do the same thing in the presence of some locomotion obstacles. So here you see that the door is actually up on a little platform that the robot needs to walk over. We sneakily throw a box in the way to get in the way of the robot. It avoids the box while it traverses the door. It can open the door while it's, standing halfway up on this platform. So this really is, directly integrated with the underlying motion capability. If you watch closely there, when the robot backs up to pull the door open, it actually has to step all the way down off of the platform. And again, avoid the box when you're going through. As I said, there's a semi-automated version of this that essentially shifts responsibility for doing things like, the detailed grasp planning and doorknob recognition off of the core software we have on the robot off to a client or user, so that you can deal with more complex door handles or door geometries. An obvious, we have made no effort to deal with opening glass doors that the robot could see through, where its sensors don't actually sense the door well. So there's an obvious application there for a little more off-robot smarts and capability. As I mentioned, we have a dragging mode for the robot. So this is, again, you use those same grasping tools to go engage with an object. And then you simply drive the robot in reverse. We have cameras all the way around the robot, so that's actually not that difficult a thing to do. And you can, drag the bench across the floor. Interesting things that are happening. You can, drag the bench press stand around in our gym. The robot's adjusting for, the forces that it's experiencing from the object. So it's adjusting its gait as well as doing its best to control arm pose. Most of these objects are actually significantly heavier than the arm is capable of handling itself. So it is in a relatively compliant mode, so that when, in particular, that barbell flips over, the arm just adapts to the posture of the thing that it's dragging and is able to successfully continue to pull on it. Next up, we have these constrained manipulation capabilities. So this is things like turning valves, pulling levers, opening drawers, even doors fall into this category. Again, we use those same grasping tools to engage with the object, and then over the API or through the user interface, we'll control the speed or the force of the interaction manually in order to go ahead and execute a task. The robot is automatically figuring out what the affordance is in the environment and adapting the impedance that it's applying to the arm in order to conform to that affordance and successfully perform the task. So here we're just turning a relatively simple crank, but you see this is the same class of behaviors that we use to do the valve turning and the switch flipping. The underlying technology here is actually an impedance controller that's running actually on both the arm and the body of the robot. So the whole thing is actually complying in a smart way to those environmental interactions. Last up, we have this 4K camera on the robot that we're using. Allows us to perform inspection tasks, so we can go, spot the dripping green goo relatively reliably. And this is using that drive the hand capability that I mentioned initially. So what do? You can put this all together, and one of the cute little demonstrations tutorials we put together is what we call, play fetch with spot. So this is a off-robot script connected to a machine learning system that's allowing the robot to play fetch with Andy Barry. The robot is, using a classifier to go find this dog toy on the floor. Once it finds the dog toy and picks it up, it looks around and it finds his legs and it goes over and walks in front of him. We always stay 2 meters away from people, so the robot stops relatively far away from him, drops the toy, and you repeat. Point is, something like this is relatively easy to build. This is something that got built over the course of, I think it was 2 half days over a couple weeks by like 2 engineers using all of the tooling that we have in place and available. So I'm going to stop there. I think I'm just about on schedule. Just want to let you guys all know we are continuing to grow and are hiring for a variety of roles. So we're looking for manipulation people, perception people, control systems people, people are interested in doing UIs, and general software engineers. Thanks, everyone.
Thank you all. Thanks a lot. It was very interesting. Yeah, thanks. It was very interesting. And of course, Spot is a very impressive robot, and the feature you showed us were very impressive. We do have time for one question, and I see that Martin has a question on the chat. So let's start with that.
Yep, I see that. Yeah, I can read it. I actually am. I think I got the right technology. Anyway, so the automatic pickup object does support arbitrary orientations. It sort of has a slight bias to do top-down grasps for things that are laying on the floor. But if we were picking up, a coffee mug that was sitting on a table, it will generate the sort of, traditional grab the handle grasp. And if you really want to be sure that the robot does that, then, you can go ahead and specify that in our grasp wizard manually.
All right. Sure, please go ahead and read the second questions and then the last one.
Yep. So the second question was for the valve switch turn tasks, is the client specifying how far to turn? The client is specifying the velocity and force level. And so by specifying the velocity for a period of time, you are also specifying how far to turn. Currently, we're going to add some features that allow you to, say explicitly, I want to turn this thing 90 degrees. Yeah, Neil, we are doing local grasp optimization. Well, it depends which mode you're in. If you're in that sort of wizard mode where you're specifying constraints, if you want, you can specify all the constraints and leave the robot essentially no freedom. But there is a grasp optimizer that's using whatever freedoms are left in order to, basically choose the best grasp posture.
We have many questions, but in order to stay with the time of the workshop, I would like to interrupt a moment, if possible. But you will be part of the panel discussion later on, right?
Happy to answer other questions later. I'm gonna.
And that's great. So all the questions that are here, we will read them later on, and please keep. I invite you all to keep writing them in the chat, and we will read them during the discussion. With this said, I would like to move on to the next speaker, who is Janet Bog. If Professor Bog can put herself on the presenter, just dragging her icon on the presenter icon. Perfect. All right. A very quick introductions. Professor Bog is an assistant professor of computer science and robotics at Stanford University, and she's directing the Interactive Perception and Robot Learning Lab. Her main research focuses are on perception and learning for autonomous robotic manipulation and grasping. And today she will give a talk on online recovery from failure. Janet, the stage is yours.
Thank you for the nice introduction, and thank you for inviting me. I hope you're seeing my slides. If not, let me know. Perfect, thank you. Okay, so today I'm gonna talk about our work on online recovery from failure, which I'm very interested in because robots are making so many mistakes all the time. And wouldn't it be great if robots could just autonomously perform multi-part assemblies, like putting together your IKEA furniture or just flexibly assemble objects on manufacturing lines? So that's really what we're interested in solving. And the main challenge towards this goal is finding robust methods for sensory motor control under uncertainty. And uncertainty can be caused by many different things. So, for example, by any kind of inaccurate perceptions, such as due to the inherent noise in robot sensors. Uncertainty can also be caused by imperfect control, such as due to limitation in the frequency with which we can send control commands to the robot, or whatever makes a robot not the greatest. And uncertainty can also be caused by manufacturing inaccuracies in an assembly due to the tolerances with which they were made. So I think we can safely say we always expect there to be some failures. And the question we ask in this particular work I'm going to talk about today is how we can overcome them. And so the key insight that we explored in this work was if a robot can learn from failed physical interactions with an object and actually use that knowledge to recover from it. So this is like something, or we basically are looking for the behavior that is very similar to what this toddler in this video is showing. So our insight is really that a robot could also use detector sensory motor traces from a failed interaction during an insertion to gain additional, more precise information about any kind of object properties than if this robot was using vision alone. So I just going to play this again, right? Like this toddler here, for example, creates a sensory signal that would not be there if it was just looking at this shape sorting task. And the sensory signal can be kind of motion, tactile sensory traces, sound, or just whether the shape was successfully inserted or not. And the signal also really depends on the toddler's action. And so the idea that physical interaction with the world facilitates perception of the environment is called interactive perception. And this interactive perception creates a signal in this combined space of sensory data, actions, and over time. And the interesting thing in robotics is that we have actually control over these actions to purposefully create the signal in that space and to check any hypothesis about what we're seeing. And we wrote a survey about this concept, which basically provides a framework to think about this idea, and feel free to check it out. And so also in my lab, we have presented methods on actually fusing vision and touch for insertion tasks. And I can maybe briefly summarize this here. So in this specific work, we collected self-labeled data through self-supervision, which takes about 90 minutes to collect 100K data points. And we use then this data to learn a multimodal representation, which takes about 24 hours on a cluster, but it's done fully offline. And then afterwards, we can learn new insertion policies for this peg insertion task that we explored here from the same representation, which only takes like 4 hours training on a real robot from scratch. But the main assumption that we made in this work is that one of the assumptions that we made in this work was that the robot knows that eventually the peg that it's holding in its hand will fit the hole, and it just needs to try basically hard enough. And so in this talk, I really want to talk about how a robot can even notice that it's attempting to fit a peg into a hole that will just never fit. And there are two works which are most related to our project. And so one is from the field of assembly tasks, and this is the work by Kevin Zucker et al. That was called Form to Fit. And it also addresses the task where the robot must figure out how to assemble an object under uncertainty about whether this object is, what exactly this object is going to fit. And the authors use vision and some clever ideas to recognize what matches what. But however, unlike our approach, Form to Fit requires a human intervention in order for the robot to recover from a potential failure. And then there's, from the field of learning from failure online, there's work from Lee et al., Bayesian policy optimization for model uncertainty, that uses a Bayes adaptive Markov decision process to formulate control tasks. And like our approach, it learns a set of, as I will explain later, it learns a set of differentiable filters to estimate the state of the environment online. So our work, though, uses explicitly haptic information to update the belief over the environment, which we and others have shown to be an essential source of information for manipulation tasks on top of vision. So the focus of this project is these kind of object fitting tasks, or kitting tasks, if you want, where the robot does not know with certainty the position and type of objects in its environment. And we decompose this task into a high-level object matching task, where the robot attempts to find an object in its environment which fits its grasped object, and a low-level fitting task, where the robot then attempts to fit the grasped object with a chosen object in its environment. Okay, so let's talk a little bit about this high-level matching task and how we modeled this. So we formulate this high-level matching task as a partially observable Markov decision process. And here the robot maintains a belief about the state of each object in its environment. And the belief is composed of a multinomial belief over object type and a Gaussian belief over object position. And the belief is, we just assume, is initialized, for example, using a vision-based object detector. So this could be, for example, the same technique that was used in this Form to Fit work. But there may be errors that this vision-based detector makes. And so let's talk a little bit about this high-level policy of actually picking the correct object. So it's composed of 3 steps. And in the first step, the robot selects an object from its environment, which it believes fits with the grasped object. So it's basically looks at this object type multinomial belief that it maintains and picks the most likely one. So in our formulation, the states of objects are described independently of each other, and therefore a greedy approach to object selection is actually optimal, So this means for step 1, the robot chooses basically the object for which it has the highest certainty of fit, according to its current belief that we represent with this multinomial distribution. And so after choosing an object in step 1, the robot moves to step 2, where it moves to an initial position to interact with an object. And the robot moves to the mean position of its current belief for the object it has chosen to attempt this fit. And so then the robot performs a trial of the low-level task, and it collects now this tactile sensory motor trace from its interaction with the object. And the trace is composed of the changes in position, velocity of its end effector, measurements from a wrist-mounted force-torque sensor, and the actions it performed during each time step of this trial. So you see this here on the right side of the slide, how this kind of looks like. And so our approach is kind of agnostic to the low-level insertion policy, but just for simplicity, we used like an open-loop spiral search with injected Gaussian noise, as kind of visualized here on the right. And the policy, the specific choice is parameterized by the speed at which it rotates and the speed at which the radius of the spiral grows, and so on. So we just found this policy generalizes pretty well, and so we picked it, but you can pick any other one. Okay, so now the robot has attempted this insertion, and after performing this high-level action, if the robot has failed, then it can use this information from this tactile sensory motor trace, even from a failed attempt, to update this belief about the position of the hole, but also about what type this hole has. And so the way we do this update is basically by using differentiable filters to process this tactile sensory motor trace. So these are differentiable Kalman filters to estimate object position, and a differentiable histogram filter to estimate object type. And why are we using these differentiable filters here? This is because it's very hard to write down a generative model that would be typically used in a Kalman filter that, given a certain object shape and the sequence of action, will generate a realistic tactile sensory motor trace that can be compared with the actual one. So instead of doing that, which is very hard or maybe even impossible, we decided to learn the inverse of such a model through these differentiable filtering frameworks. And so the filters in our experiments are composed of 3 components: an encoder, a virtual sensor, and a noise model. And so this encoder takes as input this tactile sensory motor trace and outputs a vector encoding the time series. And this encoder is just a neural network with 1D convolutional transformer decoder layers. And then each filter is composed of a virtual sensor, which takes the encoder's output as input and outputs an estimate of the position of the object. And this is basically our observation in a standard Kalman filter. And and this sensor is just a bunch of linear layers with skip connections. And in addition, each filter is also composed of a noise model, which outputs a vector representing basically this observation uncertainty. It's basically the diagonal of a noise covariance matrix. And these filters are trained by initializing a prior belief about the state of an object, given the current weights of these learnable layers, and then performing a filter update using the prior and a collected tactile sensory motor trace. And so to train the filters, we minimize the negative log likelihood of the true object state with respect to the resulting posterior belief of this running this filter update once. As training data, we collected a data set of 3,000 20-second interactions, and during each interaction, the actions were selected randomly, so not according to the spiral search, and an equal number of interaction was collected for each possible object type pairing to train this. Okay, so this is kind of how our method for this online recovery from failure for these insertion tasks looks like, and I want to talk a bit more about the experimental results now. So for our experimental setup, we simulated a multi-shape peg insertion task that you see here. We used RoboSuit and Mujoko. And in the simulated environment, there could be up to 5 peg hole boxes with 3 different shaped holes. And the robot basically need to figure out which one is the correct one, which one matches the object it holds. And we simulated a vision-based object detector using a uniform prior for object position, which could be up to 2 centimeters away from the object's correct position, and a uniform prior over object type. So really the main idea, just to reiterate this again, is in using this tactile sensory motor trace from failed manipulation attempts to estimate object properties. And we really wanted to know if this is possible. And specifically, it allows the robot to decide the cause for a potential failure. So it can decide whether it has failed because of trying to fit the wrong object, or that its manipulation policy was maybe ineffective. And so as a first experiment, we wanted to answer the question of how well our approach actually estimates the position of objects from these sensory motor traces. And for this experiment, we performed 100 trials where the robot basically interacts with a random peg hole for 5 consecutive steps. And in this figure, the y-axis describes the position error of the robot's belief at each time step. And we compared our approach to what we call here a frame-by-frame approach, which basically also uses a tactile sensory motor trace from a failed interaction, but it's not updating its belief probabilistically or sequentially or anything. It just does a frame-by-frame estimate. And so you see that the error of these pink bars, which corresponds to this frame-by-frame approach, is much higher on average. And so our results suggest that unlike this baseline, our approach is able to quickly decrease the error in the robot's initial belief about where the object actually is. So in the second experiment, we wanted to answer the question of whether this improvement in position estimation leads to faster insertion. And so we performed 150 trials for this. And during each trial, the robot basically interacted with a peg hole, which matched its grasped peg for 10 consecutive steps. So you want this to be higher for an increased number of steps. The y-axis is the success rate. And our approach is the blue line at the top, and you see it outperforms all the baselines, both in terms of speed and consistency. And so overall, our approach is able to use tactile sensory motor traces from failed interactions to make the robot robust to 2 failure cases. So in this first attempt in the video, we see the first failure case of basically choosing the wrong hole. And after this first attempt, the robot uses the trace from the failed interaction to understand the reason for its failure. And so it moves onto another hole. And so in its second attempt, the robot interacts with the correct box, basically, but it's unable to achieve fit. And again, the trace provides useful information, allowing the robot to understand it should attempt insertion again with this at the same place, but better, basically. And so at the third attempt, it's successful. So our results also indicate that our approach learns from failure using tactile sensory motor traces, such that it's able to more quickly accomplish also multi-part assembly tasks like a sequential peg task in this video here. Right, so this was work that was actually published at ICRA, and we weren't able to yet put it on a real robot setup, so we hope we're going to be able to do that in the future now that we can go back to the lab. And we are also interested in investigate tasks where you have more in-hand pose uncertainty and where the object's positions are maybe not fixed in the environment, or where the configurations are actually more complex. Just in case you're interested to read more about the details, this is the title of the paper, so check it out. So this was really about enabling the robot to overcome failure in manipulation tasks and learn something from failures. Really, it's supposed to basically not just give up and always need human help, but really, even if failing, trying again and then trying better. So overall, we see this idea as a step towards overcoming inevitable failure cases and thereby provide a like a way to more flexible, maybe manufacturing, where you don't need to control the environment as extensively as you may need to do today. So thank you very much for your attention, and I thank all my funding agencies and the students who have done all the work. Thank you. Thanks.
Thank you, Janet, for the talk. That was very interesting. If anybody has questions, can write it down on the chat, or can even join here the orange boxes that you see on the bottom right and ask it directly yourself. If not, or while people are thinking about it, I have a questions. In this that you showed us, in this case that you showed us, I was wondering, are the failures something known, meaning you were able to handle just a certain set of failure that you were aware before of, or can you handle any kind of failure you think, or what's your goal?
Yeah, so I think the failure is in a way defined as like not actually successfully inserting, right? It's kind of defined by this task. And so we don't have anything more fine-grained than that. But of course, it's only limited right now, or basically our experiments are only showing this right now for the specific insertion task. Does that answer your question? So we didn't really look more deeply than this.
Sure. No, that answered my questions indeed. I was indeed wondering, so, I mean, everything that is not successful, it's a failure, and so you can handle any case. So if the block drops, or if you just don't push in the right position, and all these kind of things can handle, and there is no assumptions on the failure.
No, there's no assumption on the failure other than in simulation, the peg is actually attached to the hand. So, for example, there cannot be any uncertainty in the hand right now. The way it's simulated, for example, that doesn't happen. It's so, again, like, yeah, it's pretty it's basically the kind of failures that I guess are happening is that it kind of just slips off the side of this box, or it just doesn't achieve fit because it just didn't have quite the right orientation and things like that, right? But yeah, there are no specific assumptions about that.
Perfect, thank you. There is actually a question on the chat from Tariq.
Yeah, what are the challenges for transferring the learned base filters to the real world? And do you think it's possible with no real world data for context-rich tasks? Yeah, that's a very good question that we couldn't yet really look into, so I can just give you a hypothesis. It's certainly, I mean, I think one thing we know is that it's really hard to close maybe the sim to real gap specifically for tactile data, so data from a voice talk sensor, for example. So in that related work that I presented from our lab, this work on making sense of vision and touch, we did have all our larger scale quantitative experiments in simulation, but in the end, none of these policies we transferred to the real world, right? We directly trained on the robot because we knew this is not going to transfer well. So I think we probably would need to, again, collect interaction data, just as we have done in simulation, to train these filters. But I would hope that, just like in our prior work, that this could be some pretty simple way to maybe collect this. So, for example, in our prior work, we also had like some strategies to just collect this data, and it took not that long to collect a lot of self-supervised data to just train the filters and then use them. That would be my guess. So there's another question, if there is time.
Yes, please.
Is that okay? Yeah. Would it be possible to classify failures using the structure example given jamming versus misalignment? Yeah, I think that's an interesting idea because you could, we only did like, in a way, binary classification. So if we had, probably we could take the sensory motor trace and have more classes, right, than just, for example, object shape. So our classes were basically what's the object shape, and then a regression task for the estimation of the position. But yeah, you could probably also say something about the failure case. So yeah. And then maybe pick more smartly a recovery strategy as well.
Perfect. Thanks a lot. Will you be able to join us in the discussion later on or not?
Yes, I'm happy to stay. Yeah.
That's great. Then more questions later on. Thank you. Thanks again. All right, now we are at the third and final speaker of our session. If Professor Tedrake can drag his icon on the presenter. Perfect. And so Professor Tedrake is a professor of electrical engineering and computer science, aeronautics and astronautics, and mechanical engineering at MIT. And he is also the vice president of robotics research at the Toyota Research Institute. In these days, Russ is primarily interested in bringing the rigor of systems theory to robot manipulation. And today he will give a talk on rare events, dynamics, and fleet learning. Russ, the stage is yours.
Thanks, Diego. And fun to see so many familiar names in the attendees list. So. Yeah, I read the workshop synopsis a few times trying to decide what to talk about. And I tried to embrace this idea of what can, some basic research questions that we might try to help close the gap to industry. So my short list, not an exclusive list, but just what I thought I'd talk about today is this idea of finding the rare events. I'll spend most of the talk on that. And then maybe dynamics matter, and just a teaser for fleet learning. So 3 basic research questions, right? So the first one, which I think was paramount in the workshop plan here, was how do we establish confidence in a machine learning based manipulation tool chain, right? And I think that's a hard question. Lots of us have been thinking about it for many years in many different ways. I'll talk about one risk-based framework that I think is particularly promising. It's maybe our best shot, or my favorite shot at a really, really hard problem. And then I want to address something that I've been hearing just from the conversations I've been having with people that are trying to make robots do things, for profit. And I feel like I'm hearing over and over again that although motion planning, of course, it works very, very well. It's leaving something to be desired, and increasingly people are up against dynamic limits and asking, how do we get more optimal trajectories out of our motion planners? And so, although when I first came from legged robots to manipulation, I was kind of, I said, oh, it's all quasi-static. Dynamics don't really matter here. Maybe dynamics do actually matter in manipulation. I'll say a few words about that. And then I do think this question of fleet learning, like as we're about to, are we approaching our watershed moment in robotics where we get enough data from enough robots doing interesting manipulation tasks that something big happens? At very least, if we're deploying these robots, what should we be doing with all our data? I'll spend most of the time on this first one. Okay, so here's a risk-based framework for manipulation, and let me set that up with a slightly, an example I've been using for a few years, but just to set the stage and set the context here. So we've been playing with a robot that could load the dishwasher at TRI. This is the basic setup is someone like Siwan will dump a bunch of random stuff in the sink. The robot is using cameras. It's completely autonomous in this case. It's going to use its cameras. It's going to perceive the sink. It's going to open the dishwasher and do I would say a highly non-trivial manipulation task. And we run these robots over and over and over again all day long. We use it to understand this fundamental question of trying to understand how do we certify manipulation, or at least establish confidence in manipulation that uses machine learning in the pipeline. And this was a long-running experiment that, like I said, we learned a lot from. One of the big stories, which has been mentioned a few times over the course of the day, is it's really amazing how the field has transformed in the last few years, that that we could actually do most of our testing in simulation, and we would hammer on this in simulation, extensive Monte Carlo testing, and really felt like most of the problems we saw in the real robot we could find in simulation with extensive, batch simulation on the cloud. And that included some fairly subtle bugs that were just turned up with Monte Carlo testing. And my favorite one was this example where we had a certain model for the perception system on the dish rack, where the dish rack had some variability in its pose estimation, basically. And there was a logic bug that went through our high-level task planner, our motion planner, our perception system in a very, very subtle way, where if the robot started moving when it thought the dish rack was in one location and it moved by some amount within the noise threshold before it finished moving, it could get itself effectively in an infinite loop. And that was the moment for me where it was like, wow, that was a seriously non-trivial bug that we would not have discovered if we hadn't been hammering on this with Monte Carlo testing. One of the interesting things, which I think is an important part of the conversation here, is the question of are failures rare in simulation? And that it turns out we often made the simulation much harder than reality. So we had adversarial dish racks that were, this was kind of our equivalent of autonomous driving through downtown Tokyo or New Delhi or something like this. This was like the dish rack is always bouncing around like crazy. And because we took this sort of aggressive testing and simulation approach, even when our robot was working very well with very high levels of performance in the real world, we were able to falsify it with relatively weak statistical algorithms, just naive Monte Carlo. But I don't know how far that gets us. When we really try to get industry hard and really try to drive into the multiple nines of reliability, maybe we need more. And I want to talk about what more might look like. So the risk framework asks the question of how do you estimate not just whether you fail or not just find counterexamples where you fail, but actually trying to estimate the probability of failure so you can somehow establish confidence in your system. And importantly, this framework is assuming, to begin with, black box, very high dimensional complex simulators. So it could be an entire autonomous driving stack, an entire dish loading simulation, planning algorithm, perception algorithm in a deep neural network, you name it. And we've brought online a handful of tools in a couple papers that were led by Matt O'Kelly and Aman Sinha that used a variety of tools from rare event simulation to try to bring to bear some of the ability to estimate the probability of failure in these highly complex scenarios. And they use tools like adaptive multi-level splitting, Hamiltonian Monte Carlo, and some cool tricks from normalizing flows to try to warp our parameter distributions and our sampling distributions that were modeled with basically normalizing flows. And that was a series of papers that were targeted initially at autonomous driving. So that there's a key idea that goes along with this, and as a sort of a philosophy for what should we be asking for from our testing strategies. The philosophy in this risk-based framework is that we should be asking for failure probability instead of writing an algorithm that just tries to find counterexamples. And the reason for that is subtle, but asking for the probability of failure is a harder question to ask of an algorithm. It's a harder inference. But the result is potentially very powerful because it instead of falsification algorithms, which are not designed for coverage, a failure probability, in order to estimate that quantity accurately, it actually needs to find diverse counterexamples. Okay, so this is a very simple cartoon of just, let's say you're minimizing you want to find you have some noisy function, it has many local minima, and you care about when it goes below the blue line, okay? So there's two different questions you can ask. The old one is just find me some X that's below the blue line. And that's the falsification question in assured autonomy, if you will. And the harder question is estimate the total probability, given some probability distribution over X, what's the total probability of being under that threshold? That's clearly a harder question, but it brings nice advantages. Okay, so although there are many local minima, many places that dip below that threshold, we don't want to just find one of them. We want to somehow find coverage of them. And even that, once we have a probability distribution over the space, we'd like to find somehow the most likely failures. Okay, so even if there's a number of failures in the tails of the distribution are somehow below that curve, we don't want to find just the super rare events. We want to find the most likely failures. And both of those ideas are captured very nicely in this sort of estimate the probability of failure framework. Okay, and we'll do that with these learned samplers and normalizing flows and the like. So give me a quick thumbs up if that idea landed. Let me get a little feedback here. Does that idea, this idea of asking for the probability of failure instead of just random samples? Awesome, thank you. That's a good feature. Okay, so there's a bunch of tools that we've brought to bear from importance sampling, from rare event simulation. I won't discuss all of them here, but I'll just give you a taste with the idea of multi-level splitting. Okay, so let's say I've got a Gaussian distribution sampled around the origin. Okay, and I want to find out the cases, the number of samples, the probability of getting a sample that's off in this box here. Now that's many standard deviations away from the unicovariant Gaussian, so it's going to be a very low probability of getting any samples in that box. Okay, so how do I ever sample from that box? Pulling random numbers from the Gaussian distribution is a lousy way to do it. A simple idea here is to do these multi-level splitting. So what you do is you try to find versions of this box, which are sort of increasingly close to the origin, which you can sample from with high probability. Okay, you take your Monte Carlo sampler, and you basically, whenever it's getting some features that are on the way to this failure, you'll now define a new distribution sampled in that vicinity and use the locality to basically make a smooth ladder of samplers that slowly warp the sampling distribution from the original Gaussian into one that with high probability samples from your rare event. Okay. Now there's ways that that the field has tried to adapt gradients if you have them, to do these normalizing flows. There's all these different ideas that make this more powerful, but that's basically the essential idea, is that you're going to try to find an important sampling strategy that will draw your sampler towards choosing taking samples from the failure cases. And Matt and Aman applied this almost exclusively in autonomous driving, but it was successful beyond my wildest imagination. So they had what they did to really prove it, in my mind, was they took the comma.ai open source open pilot. They put it in the Carlos simulator. They ported it to the Carlos simulator. They started varying crazy parameters like time of day, lighting parameters, where the other cars are on the road, things like this. And through this failure search, they found diverse rare events that were like surprisingly subtle. So if I just play that one again here, the reason that this collision happens is because the sun flares into the perception system's camera, causing it to misjudge the distance to that car and then eventually run into it. Okay, and it turns out that that bug, similarly, if you look at the output from the autonomous driving system, the open pilot system, it's actually like Jeanette, it's carrying a complete belief distribution over the distribution of the other cars. And actually its distribution got very, very wide, which is the correct thing to do. But its motion planner somehow just took like the median of it or something like this and ended up driving right into the vehicle. So I think the perception system, the belief quantification was doing pretty well. Yeah, it's just a simulation, but who knows? Okay, so, Matt and Aman created a startup, Trustworthy AI, and they were just acquired by Waymo, so that was awesome. Kind of a kudos to them. So, but I do think it says that they were onto something that was super good. So let's reflect for a minute on this risk-based framework. So I think a lot of us would agree that certifying, like in an absolute sense, verification, verifying a manipulation system of this complexity is probably a fool's errand. That's asking for too much to say we have 100% confidence. So I think we want some sort of probabilistic confidence, probabilistic guarantees. This work sort of convinced me that empirical risk estimation, which I would have considered to be a very, very hard problem, with a lot of room for improvement, but there's hope that it can really scale to high dimensional data. That was an open question when I started thinking about it with them. And I think if you want sort of a plausible formulation of safety in difficult domains, this is my favorite one so far. I mean, I think we can say some things in absolute ways about neural networks, even in, if they're small enough, or there's other things. But I think if you, in a practical, putting all this complexity together, this feels like closer to the right question to be asking. And even if you don't believe that it will ever certify a system to 5 nines, you don't have to. I think it's immediately useful as a development tool. If you're in industry, or if you care about having a system that's very robust, this is a great way to spend your AWS cycles running simulations that will find failure cases, diverse failure cases more quickly. So I showed the autonomous driving case. How would you make that work for manipulation? And there's a whole set of tools that you can kind of build up around this, okay? One of them would be, how do you define distributions over manipulation scenarios, okay? So we've done work to sort of, with Taku and Cooney and Ben and Ludwig have been doing work on parameterizing simulations to study distributional robustness and distribution shift. So that's one of the great things about simulation, is you can really dial in the distributional robustness questions. So for instance, we've made, in the dish loading scenario, we carefully parameterized procedural mugs. So we could generate from procedural CAD a whole infinite family of continuously parameterized infinite family of mugs, hit them with a texture map. My favorite two are TRI and MIT texture maps. Anything you grab on the web, you can stick on there, throw it in simulation and start testing. We've procedurally generated a bunch of weird things. I mean, my favorite is we have like procedurally generated vegetables, potatoes and cucumbers and you name it. We've also, of course, done the same sort of things that they've done in autonomous driving, where you change the initial pose and you change the lighting conditions and the like. And that's a super rich source of testing for these systems too. Separately, but related, we've been working on models. Greg has been working on models of using the language of scene grammars familiar from computer graphics to give structured parameterization over distributions of scenes. So you can write down a procedural model, that you might write in code, but you can write it in the language of the scene grammar. It gives a very nice way to describe somehow like the ways that objects are spawned in the simulation, with some probability distributions on the rules, and also the continuous parameters of what's the pose and the shape of the object and the like. And this is, this feels like a language that is sort of sufficient for specifying a lot of our tasks, but also penetrable by our more advanced sampling strategies. Okay, so we went to apply all of this to our manipulation pipeline, and Wei decided that he wanted one more piece. So I think that actually could be enough to start doing testing, but to actually put our local systems under test in the RISC framework, Wei added one more important contribution, I think, which is thinking about the distributions that you can't write nicely in this way. So I used mugs as an example, but actually mugs is also one of Wei's favorite examples of what's hard to write down with a procedural model. So it's very hard to think about. I mean, the shape of mugs, we wrote a fairly good one, but if you go to the Disney store, you'll find some weird mugs out there, right? The textures, I think, are infinite. So how do you write that distribution? And Wei's idea has been to combine the structured parameterization, the number of objects, the object pose and the like, with some empirical distributions, which are just a data set, a collection of images that you've captured off the web or off of real mugs. And those might capture the things that are harder to model in the structured way. So object shape is on the boundary for mugs, but for some crazy shapes, it could be a very useful thing. Texture maps is a great example, I think, where images are easier to just have a batch of images than to try to write a continuous parameterization of the possible images. Okay, so how do you apply MCMC strategies, these Monte Carlo sampling strategies, to those semi-empirical distributions that have some continuous variables and some discrete variables? Well, the piece you need is you need some sort of a distance metric, something that tells you how do you sample from similar examples to the ones that I'm currently sampling from. And Wei's insight was that the latent space that you can get from an image classifier or something like this is a natural place to write a distance metric on the latent vector z. You know, just use some sort of Euclidean metric on that latent vector as a distance between possible images, and then you form a graph, a weighted graph over all the possible images in your data set, and your sampling strategy. He's got a nice algorithm that sort of walks the graph in order to find similar counterexamples much faster than a random just checking all possible images. So Wei's goal was to evaluate KPAM, which was one of our recent sort of key point-based manipulation pipelines that Lucas and others, I think I saw on the call, were involved with or created when they were in the lab. So imagine just a manipulation system that's taking key points in. So it has a neural network doing a key point estimation using an inverse kinematics system and a basic motion planner to do the actual manipulation task. We use this for a lot of different examples in the lab. Shoes and mugs were the canonical ones. Okay, so in this setup, the structured part of the distribution is the object pose, scale, and illumination. And the empirical distribution was just the object textures. So we took a bunch of images. In fact, Wei did a lot of experiments throwing MNIST images on as mugs. It's like the ugliest mugs you've ever seen, but they're MNIST images on texture mapped onto mugs. Okay, so and then he tried to do empirical sort of rare event estimation on the key point detector by itself and then on the whole system. So if you did the key point detector by itself, you can just give it a risk, some failure that if your L2 distance on key points is too large, then you call that a failure. If you compare his sampling strategy to the more naive one, which is trying to combine, it does the smart thing, the existing rare event simulation on the continuous variables, but it's just sampling the images at random, not using any distance metric between them, then you can do 10 times better, roughly up to 10 times better with his extra graph heuristic. That's just a taste of this idea, but I think there's a lot of work to do and sort of use these tools in our manipulation workflows. Interestingly, when he went to apply it to the entire KPAM pipeline, the motion planner failed way more than the perception system, which is just, that's not supposed to be that way. But hey, perception's gotten really good. And let me just say one more thing about this, about the scene grammars before I move on. But there's a really nice question about how do you take failures in reality and bring them back into simulation. And companies like Waymo and probably Boston Dynamics and the like have tool chains that do that. A customer sort of says this thing failed. I'll reproduce this on my robot. I'll put it into my simulator and add that as a test case. Is there any hope? I think some of these tools can provide some hope to generalize or automate that. So the scene grammar language in particular is compatible with variational inference. So if you get a raw data, you can ask what was the probability, what sort of possible event creation probabilities and pose samples would have generated that. So you can explain the raw data with the generative model. And then you can try to fit the parameters of your generative model to your observed worlds. So this is just a toy example of the place settings here on a table, but you can imagine sort of calibrating your distribution of simulations to real data. And I have to believe that it's going to be useful in the long run. Okay, let me finish with just a quick comment about beyond sample-based motion planning. So the shortest path on graphs of convex sets is an idea I can just give you a taste of very quickly. So what motion planning does industry actually need? I think we've seen many examples of diverse inventory, of people trying to manipulate a lot of variety of stuff. And that implies you need a lot of diverse different motions. You probably need a motion planner, not just pre-recorded trajectories, but they're in relatively consistent environments. This is an example of food end of service, sort of point of service food manipulation from DexI. And oftentimes speed equals money. So you really want to move that robot fast. And I really think in research labs, we often overspec our robots and don't think about these things. But when you get closer to product, you try to cut out some of those margins. And I'm hearing over and over again that people actually are up against torque limits, speed limits, whatever, and those are hard to put into a sample-based motion planner. So I know I've talked a little too long, but let me just get the big idea here is that while a lot of us are doing sample-based motion planning, I think we can do a lot better if I can just give you this one picture. Okay, so we've been doing a lot of work now on optimizing shortest paths on graphs of convex sets. So a probabilistic roadmap, you sample a bunch of possible configurations, you make a graph on them at runtime, you actually try to find the shortest path on this graph. Okay, but you have to put in potentially a lot of samples and then optimize this after the fact, and that can be painful. So it turns out you can do better if you switch from this problem formulation, I think, to switching to this problem formulation, where instead of having sample points, you sample regions. This would be in the motion planning problem, regions of configuration, free space where you're out of collision, and then inside these regions, you have the ability to do some strong optimization, optimize the dynamics. And that's the kind of thing that we've been doing for a long time for optimizing dynamics of, let's say, quad rotors flying through space or the like. And I think it's maybe time to bring those over to manipulation. I feel like we haven't emphasized that yet but there's good tools that we should be using. Okay, so let me not go through all the details of that, just to say that you can really just decompose these sets quickly, and just imagine if you're a robot trying to manipulate something around shelves, then you should first just decompose the space into a bunch of, let me see if I can find the good ones. You can find the big configuration space regions that sort of summarize where your robot can move, and then you plan with those instead of with points. Okay, I'm going to skip fleet learning, sorry. But there's my 3 questions. Let me just end and say that we also have job openings on soft manipulation at TRI. Please look at the website if you're interested. And there's a fall manipulation class that some of you have taken, I see, on the call, but it's getting better all the time. All right, sorry for going a little long. That is so fun.
Thanks, Joras, for a very interesting talk. I'm sure that there are probably many questions specifically regarding your talk, but why don't we try to move to the panel discussion? In a sense, there's the discussion at the end of these sessions. So now I'm switching mode. Well, while I'm preparing it, and I will move all the 3 speakers, Al, Jeanette, and Russ, on the panel. Russ, if you want to read the question that Pete, actually, yep, that Lucas made you first, and
yeah. Okay, so the analog of the smooth ladder of samplers is a guided random walk on a graph of the images. So what you basically say is that I'm sampling from some distribution on the graph right now. I'm getting failures in this part of the graph, so I will continue to sample from that node on the graph and its most connected neighbors, and that gives you the same sort of ladder of samplers. Pete, I'm reading yours at 3 words column here, so. So that's yeah, okay. I think there's many ways to possibly quantify failure in manipulation, right? So actually, in Wei's initial experiments, he went in at first just trying to verify the whole pipeline. And then I think I've heard him and many other people sort of say it's worth breaking these down into the component level verifications. So he really did want to verify the key point estimator as an independent component first which had a very natural metric of L2 distance on the key points, and then the perception system, the planning system. Unfortunately, the metric was SNOP Info 13, but that's not the long-term answer, of course. I think in general, the verification community thinks a lot about taking strict failures like cars crashing and writing a smooth risk metric that tries to, that's awesome, thank you, that tries to smooth that out a bit. I know we're
another question from Louis. Yeah, there's. I just want to invite everybody to ask questions now to all the three speakers. And I mean, Russ, if you want to answer this question of Dewey, and then maybe we can go to some more general questions.
Yeah, sounds good. So I think that people are moving their are trying to move robots fast enough that the dynamics matter again. That the limits of performance are the friction cones at the end effector before the object slips out, the torque limits on the joints, the speed limits, acceleration limits on the joints. And I think, many tasks are often quasi-static, but if you're trying to move, if you're getting paid by like how many Chipotle bowls you can fill per minute, then actually things get dynamic again. So.
All right. Maybe I have general questions for all the three speakers, and then we go back to the chat with the questions that are for us. There was also a question for Al before. My question is I mean, both Jeanette and Russ talked about failure cases, and while Al instead didn't touch on this point on his robotic platform Spot. So maybe my question is, well, first for Al, how in the spirit of the workshop, right? How industry in this case represented by Boston Dynamics and Spot, how you deal with failure cases, and how do you make these primitives that you used for grasping so robust? And for Jeanette and Russ, maybe how do you think that your techniques that are developing can generalize enough for scenarios that are indeed of interest for the industry?
Yeah, so the thing I didn't talk about at all is sort of our efforts for doing state estimation in these systems, and that's a key part of making them robust and successful, right? They are constantly doing their best to produce accurate estimates of continuous state, as well as looking at a variety of guards for discrete failure. So, I moved too far, my gripper closed more than I expected. All of those things are fault triggers. And then we use those in a sequential composition kind of framework to automatically do retry and fallback to make the overall system as robust as possible.
Does that state include the valve state, or is that really only robot state?
Right now, it's only robot state. We've talked about doing it for valve state, and we're not quite sure how critical that is. We think robot state is a pretty good surrogate for valve state, because valve state is not sort of directly observable.
Right. It gets a lot harder, right?
Yeah.
Especially if it's like...
I think that's a good question, and we are sort of avoiding it to get systems that are as robust as possible in the short term. But I think that's a good open research question. Diego, does that?
Thanks all. Yeah, I think that answer. Do you also want to talk about something, how you can see your techniques?
I mean, my sense is that...
I'm not saying to Spot, but it's something similar that can convince you to use your techniques.
I think Al's team has done roughly what we're advocating. I'm just trying to, I think it probably was very engineering expensive to do. And so I think if we could, I think hardening a system by trial and error on the real robot is, I think if you have really good robots then and can fix them quickly and stuff like this, then it's less of a cost. But I think the future, we want to be able to do that more and more automated. So we're just trying to shorten that cycle time so the next company can come and do it.
Thanks.
Yeah, I wouldn't say it's been extremely expensive for us, but it's absolutely not cheap. Right, there were.
But it goes back from early days of hammering on the door task and stuff, right? I mean, you've amortized it over years and years, probably, right?
Yeah, and the door task was, there were years of discovery of what is really the task for door opening and what does it mean to really make door opening robust. I think the latest iteration of door opening was probably about, something on the order of 3 or 5 person months of effort to make it fully capable and robust. And that was to get to, a version of it that we were comfortable delivering.
Yeah, maybe to Diego's questions, you were asking of how some of the techniques can be scaled up to more general scenarios. And just maybe coming back to the things I've discussed, I see the specific task I presented as an instance of deciding whether you just need local changes in your policy of manipulation in this case, or whether you just need to try something completely different. So this I basically, in a way, presented this toy task of the peg insertion, right? But I'm interested in giving a robot the ability to be able to do that, deciding between just small adjustments or not. And I think there's like a question on how do you view recent developments of RL for manipulation? I think what I found is that where RL is really helpful is to make these really hard to model local adjustments. For example, in these insertion cases, right, where it's really hard to just model or find a good strategy of just wiggling something in or assembling something, or maybe really aligning that gripper with the right way to do that manipulation task. But global adjustment, I'm not so sure, or like long horizon reasoning, I'm not sure how well RL scales for these kinds of things. So I think we have some better maybe techniques for these kinds of global adjustments. Yeah. And by the way, I really like Russ's work on automatically finding these failure cases in simulation. So I was already a while ago intrigued by these automatic ways to search for adversarial examples in a way. But yeah, I was kind of wondering, like, so you showed some examples with real world cups, but I was wondering how many of the failure cases you find in simulation are going to be really also be mirrored in the real world, and how many do you think you're going to miss, like maybe in relation to the complexity of the task? Like how do you view that?
Yeah, that's a huge, important question, and I can only give a sort of anecdotal answer, but the philosophy again became, so the philosophy, of course, in the real world was get our failure rate to close to 0, right, and just drive it down and down and down. But in the simulator, we ended up keeping the failure rate fairly constant, because as we improved, there was like this red team, blue team thing where what the team that was fixing the manipulation pipeline was driving the failure rate down, but the people that were increasing the complexity of the simulator with all the adversarial things was driving it up, and there was like some equilibrium that was hit there. And somehow it did seem that even the pretty complicated, I'm sure we could have, if we really looked for examples in the real world that we never saw in simulation, like there were cases where the pad on the fingers would sort of tear off or something like that. We didn't simulate that, so that was just never in there. But for perception failures, for logic failures, which I think were somehow the more nuanced ones where they had multiple components interacting, I was very impressed with how well it was able to find those. And we really, and it actually went the other way. It was like the Monte Carlo test would turn something up, and we would go to our robot whisperers and say, have you ever seen this one? He's like, oh yeah, I did see that one on the real robot. Yeah, I totally saw that. And I kind of pretended I didn't, and we kept going. But I was very impressed with it.
Nice, thanks. I will try to go through some of the questions that are on the chat. I would like to start with the one that was for Al during his talk, just to go in order. If I find it, I think I went too far down. I think was this one from Arsalan. Is motion planning for hand done separately from the whole body, or everything is done along each other as whole body motion planning?
Oh, okay. Yes. Depending upon exactly what we're doing with the robot, we will either run basically a isolated motion planner for the arm. In particular, if we're moving the arm relative to the body, we run a very simple planner that helps us do that. If we're maneuvering in a tight space, explicitly trying not to bump into things, then we have some tools that will run sort of a whole body motion planning strategy. And those are very traditional tools, nothing particularly fancy.
Okay. Then there was actually a Rust question. Can Spot drive a Polaris? Otherwise,
he answered that one.
Yeah, I answered that one in text. I said, no, sorry, no Polaris driving yet.
Okay, then that was the answer.
Next time, yes.
Next time. Come back next year.
Okay, we will ask you in the next workshop then. Okay.
I do think it's super impressive. I think Spot could just do the DRC at this point, and which is really, really awesome to see.
All right. This question again from Arslan. How much is the performance gain in the whole manipulation task if KPAM is trained on hard negatives found by rare event simulation?
Yeah, that's a great question. I think we're still finding out exactly, but my initial understanding is that a little bit, of course, but not as much as I expected. So I think mostly because the key point estimator trained in simulation to begin with was already very good, and throwing some of the hard negatives of the perception system didn't make a dramatic improvement. A little bit. I mean, I'll ask Wei again as soon as I see him. But I think the first takeaway from that was that it didn't as much as I thought. And we don't. It's a conventional non-learning planner, so we didn't adjust the planner parameters based on those hard negatives.
Okay. Then there was this question from David. Actually, Jeanette already started talking about it. I don't know if the others have something to add. How do you view recent development of RL for manipulation?
I want to hear Al's answer.
I got to hear that question one more time.
How do you view recent developments of RL for manipulation?
Yeah, so I'm the skeptic in the group, right?
Yeah.
We are doing some aggressive experimentation with RL for locomotion in some very complex environments because we have no clue how to write them by hand. I think we're yet to see, applications that our customers care about where RL would be necessary in the manipulation space. But again, come back in about a year or two when the research moves a little bit further along and our customers have a little more faith in what they're doing with the robot.
Maybe coming back to what I said before, I'm wondering if it could potentially, in your case, relieve some of the levels of teleoperation and things you have to put in onto the interface. That's just a hypothesis, right?
Yeah, I think that's absolutely true. But the reality is that most of our customers are asking us for more fine-grained teleoperation and control because they don't trust the robot yet. They don't trust these autonomy systems, right? These people are trying to use these machines in. We're trying to get actual adoption at this point with Spot in some scalable use cases, and there are people using them in mission critical roles at power transmission facilities, at some nuclear facilities, and those people are pretty conservative in terms of what they're willing to.
I'm glad they are.
Yeah, correct.
Okay.
So the reality is we're fighting basic adoption and making the arm reliable and safe and controllable by them is really critical. And again, I would say this is a question we will revisit and is a great one to come back to in a year or so, presuming that we're actually successful in getting some deeper adoption.
Okay, then there is a
Russ could answer that question too, though.
Oh, I'm happy to answer or not. It's
no, please go ahead. Sorry.
Okay, so I mean, I think some things look incredibly good in RL and manipulation. I think there's going to be, I think it's very exciting now that there's a lot of the theoretical RL and the theoretical machine learning people that are coming and looking at it. I see Jack on the call, Jack Ummerberger's working on it in our group and saying, asking like, what is the reason why this works? And can we distill some of the successes into something that's maybe a more mature, more reliable algorithm, specifically for like the control through contact that we've seen, for instance. And I'm kind of optimistic that RL maybe kicked us out of a local minimum in our thinking, but that also we can have much more efficient algorithms that don't require, millions of simulated hours in order to get a good policy. I think there's much better things coming soon.
Okay, great, thanks. So next question is from Devesh. Do you think future robots can come loaded with physics engines that specify a prior knowledge about their environment to facilitate the interaction? I think this is for all the speakers. So basically, can robots come already with a physics engines inside in order to speed up maybe their interaction learning with the environment?
I think we have physics simulators and they should definitely use them. The question is whether we can simulate. I think there's not a question about whether we can simulate the accuracy of any one task, but there's a question of whether we can simulate the diversity of the world. So to say that specifies prior knowledge about their environment for any environment, I think I would say no to that. But I would say to have a sandbox of useful simulations queued up so you as a tool, I would say definitely yes to that.
I would agree with that. I mean, we run a lot of model predictive tools inside actually versions of the robot that we deliver, and those are all the utility of those is always limited by the quality of the simulation.
Yeah, I don't know. Did we lose L? No.
No, I'm sitting here.
Okay.
I was done for that.
Okay. Yeah, I was. I would say similarly. I think there are some physics biases or models that we can evaluate actually really fast, and therefore they can be put on a robot, and they're very useful. Right? We already do that, but some things are so hard or expensive to simulate that it doesn't make sense to have them on a robot. Or maybe you could use a model-based technique with a learned model. That could work, but sometimes you want to even deal with things that you can't even model in a simulator to sufficient accuracy. I think Russ just said something opposite of this, but I think there are just some things that we may want to do with a robot that we don't know actually how to accurately simulate. But anything with like funny friction, liquids, oils, or particles and things like that. But that would be my thought on this, or my prediction.
They're expensive maybe to simulate, but we can. I mean, I think we can simulate liquid-like things, right? Can I, if I use this cup and take this liquid and pour it, can I reconstruct that exact scenario? No, but I think we can simulate that class of scenarios. I could take, Flex or whatever my favorite simulator is and get something that's reasonable.
You can certainly get something that's structurally representative, right? Whether you get something that's parametrically exact, I think is not true. And therefore, you need to ensure that you actually have robust behavior underlying whatever you're really running, right? Because the real world is going to behave a little bit differently. And Jeanette, I would just say all friction is funny. I'm yet to see any friction that matched the simulation.
Okay. Yeah, I agree, I guess. Yeah, I guess maybe. But yeah, in any case, these things are definitely too expensive to put in a real-time loop on a robot, I think. So, but yeah, it's great to have it in simulation and to sandbox, use it as a sandbox for sure.
All right, thanks. Then there is a question for Russ from Alan. For manipulation tasks like the ones you talked about, do you think parameterized distributions and existing datasets are able to cover most of the failure scenarios, or we need some kind of auto-distribution robustness?
Okay, so there's a subtle point that I didn't make in the talk, but I think it's important here. So people aren't doing what I advocated yet. They're putting like zebra patterns on mugs and flipping lights on and off and whatever. I think the lesson from robust control is that if your control authority is large relative to the distribution that you're dealing with, then you can be very sloppy with your uncertainty representation. You can just kind of put zebra prints on or whatever. And I think as our levels of performance take us, as we want to be like operating more at the limits of what our manipulation systems are capable of, then in a robust control sense, you have to be more explicit with your uncertainty quantification and not ask for things that are impossible, but only ask for the things that are like that are capable for your control system. So my sense is that there's going to be a maturing process where we are only doing simple tasks where we can be very sloppy, domain randomization, whatever you want, put RANDs in your simulator. And as we get more and more advanced and we're trying to eke out the last levels of performance, then we'll try to be like, yes, there's exactly this distribution. Do we always need some kind of out-of-distribution robustness? I think maybe yes, but again, at some point the compute, if I was like, I'm going to say Nolan Ryan because I'm old, but if I was like a baseball pitcher that that's trying to throw a fastball through a small target, then I can't say that's going to be robust to the wind going between negative, from 20 miles an hour to the left to 20 miles an hour on the right. That's just not, Nolan Ryan's going to say, no, you can't do that. So it depends what the task is.
Thanks. Then there is a question for Al from Lucas. Are more autonomous, like non-teleop, user-guided manipulation tasks on the roadmap for Spot? And what do you see as the main challenges to getting there, like perception, higher level reasoning, task specifications, etc.?
So I absolutely think that they are in the future for Spot. I think the distinction we make is whether they need to be implemented in core software that actually runs on the robot or whether they run above our API. And that means that either we develop them or they're open to development by third parties. And I think that, or my focus right now is on ensuring that we have a rich enough and robust enough set of capabilities running in the core at high bandwidths on the robot so that it is possible to build those more autonomous capabilities still reliably, but with lower bandwidth requirements, basically, I'm going to call it off robot, but whether it's in a backpack computing payload on the robot or in the cloud, because you have good comms, I don't really care which one that is. In terms of the challenges, I think getting truly trustworthy manipulation autonomy that our customers are likely to adopt really depends on very robust perception and very reliable error detection and error recovery in those systems. So they have to know when they're starting to make mistakes very early on, stop doing the bad thing, and either do something smart themselves or ask for help in very effective ways. And the other huge challenge, I think, for actually making deliverable, deployable autonomy is coming up with an effective way for non-experts to program those systems. I think that's going to prove to be very challenging.
So, Al, do you see the company having to think about perception for manipulation very differently than perception for terrain?
Oh yeah, absolutely.
Because the terrain you can be sloppy and you can your foot,
Well, terrain we can get away with at roughly a few centimeter resolution. for everything, because that's about our accuracy of placing our feet. And for terrain, the scene understanding or scene classification problem is pretty simple. There are steppable places, there are unsteppable places, there are places you're willing to let the body go and places you're not willing to let the body go. And then there are a couple of like special overhangy kinds of things you have to pay attention to and recognize. But the total list of classes of things that you need to classify and recognize is countable, certainly on fingers on both hands category. I think in the manipulation space, that goes up by at least, a factor of a few, if not a factor, in a full order of magnitude.
But even those systems could make mistakes and would be hard to catch, right? If you stepped on something you shouldn't have stepped on or whatever, right?
Right. And we do that all the time, and we just rely on the fact that, the robot still walks pretty well when it's blind, right? And so even when it steps on something bad and something slightly untoward happens, the robot recovers very well, a vast majority of the times. I think your notion of, risk-based assessment for manipulation sort of makes sense, because I think there are some manipulation tasks where that may be true, and there are other manipulation tasks where the risk is unacceptable. And you need to either, you need to back up and try again or figure out how to gather more information before you decide to proceed.
Thanks. Then Lucas had also a question for Russ.
Oh, he was just ripping me, I think. Although it did make me think of like that metal finger, just attach it to Spot's head and then go like this. I think you could do it.
All right.
I know the DARPA guys worked really hard to pick that drill to make sure it was possible to turn it on with one hand.
But it's still turned off after like 90 seconds, and that's why that's why our robot died.
Before tonight, it was like 5 minutes or something. Because DeWalt said, who in their right mind would run this drill for more than 5 minutes continuous?
Only robots. Yeah.
All right. Thank you all. I think now we can move to the actual final panel session that will include also the other speakers. So we can thanks Jeanette, Al, and Russ for this discussion. Thank you all, really. It was very interesting. And okay, now I would like to ask also to the other panelists to join the panel. The panel plays on top of the screen by just dragging exactly their icon over there. Also, hi Juan. Then there should be also Matej. Hi Matej. And is Adam Norton also here as well? He didn't give a talk today, but here he is. Let me move you up here. Okay, now we have all our speakers here. Yeah, perfect. All right. Let's.
I actually have to leave. Sorry for that. But thank you, everyone. This was a great discussion. Thanks for the invitation. Bye. Thanks for the questions. Bye.
Thanks, Janex. Thanks for joining us. All right, 1, 2, 3, 4. Who is missing? Are we all here? Is Matej as well here? I don't.
He was.
See him anymore.
I'm back?
Here he is. Okay.
Okay, I think it can only take up to 5 people. So I was just saying it's going to be hard because Russ, Jeanette, and Al already tackled all the big subjects. That's it. There's nothing left.
We are going to go back and we will hear your opinions as well. No, okay. I mean, I will just pretend that this is a different session. So I would like, of course, to thanks everybody again for attending this and surviving to this workshop until the end, all the audience and of course all the speakers. It's quite late in many parts of the world, so thanks for everybody to be here. And so we can start the final panel discussions. And I think just as an introduction of what would be the goal of this discussion is that we often hear that there is a significant gap between the tools developed in academia, especially in the last decades with the progress of artificial intelligence and machine learning, with respect to the applications and techniques that are used in industry. Moreover, I think we can probably say that robotic manipulation skills that the scientific community in the overall has developed are still not at the point of being comparable to human-level versatility and dexterity. So what are we wondering and trying to understand in this workshop and with this panel is why there is this gap and what can we really do about it? Well, we already have an excellent group of speakers that with a mix of expertise in between academia and industry. Of course, we have Professor Ted Drake from the Toyota Research Institute. We have Juan Aperillo Ojea from Radio Robotics, Al Rizzi from Boston University, Matej Ciocarli from Columbia University, and Adam Norton from UMass Lowell. I know that some of you already introduced themselves before, but some not. So would you mind to just give 1 minute short self-presentations and so that everybody in the audience know who you are, if they don't already, and then we can start. You can go in any order, otherwise I will call you. All right, I'll go in the order that I see the people on the screen. So Matej, why don't you start?
Sure. Hello, I'm Matej Ciocarli. I'm a professor in mechanical engineering at Columbia University. Before Columbia, I was at Willow Garage, which some of you might remember as a sort of robotics research incubator in Silicon Valley, and then briefly at Google. But now I've been at Columbia about 7 years. But I'll draw on my experience from Willow Garage and Google to try to answer some of these questions. So thank you for having me.
Okay, Juan.
Hi, this is Juan Aparicio. I work at Ready Robotics, leading their product organization. Ready is a startup that is making the first operating system and platform that works across different robotics and automation systems. Before that, I had the luck to lead a team of researchers and engineers at Siemens Technology in Berkeley, California, where we were basically answering the question if deep learning can revolutionize the world of robotics. That was around 6 years ago, and some of the work that we did was published together with professors in Berkeley like Ken Goldberg or Peter Abil or Sergey Levin, and we also work in Stanford with Janet quite a lot.
Al?
I'm Al Rizzi. I'm Chief Scientist at Boston Dynamics. I've been at Boston Dynamics for 15 years. In those 15 years, we were, an independent research and development contract house. We got acquired by Google and shifted out of that business and became, Google researchers looking for ways to commercialize our technology. Google sold us to SoftBank, who really helped accelerate that effort and helped us focus on actually getting initial products out. And then just recently, we transitioned to being 80% owned by Hyundai Motor Group, which we're excited about because it's nice to actually have a parent who knows how to build things. Prior to Boston Dynamics, I used to be faculty in the Robotics Institute at Carnegie Mellon. Adam, over to you.
Hey, everybody. No, I'm coming in kind of at the last session here, but I'm Adam Norton from the University of Massachusetts Lowell. I'm the Associate Director of the NERV Center, the New England Robotics Validation Experimentation Center, supervised by Holly Yanko, noted HRI researcher. So I basically run a test and research facility that is all around the development of evaluation methods and metrics for robots of all different types, including manipulation systems, mobility systems, aerial vehicles, pretty much everything except for surgical robots. I also serve on the ARM Institute's Metrics and Evaluation Working Group, one of the co-chairs of that group. And I know Arnie gave the opening statement to this workshop earlier today. And excited to hopefully provide some insight into test and evaluation of these systems.
Thanks. Russ?
I'm Russ, professor at MIT and the VP of robotics at Toyota Research Institute. Worked on legs for a long time, flying things for a while. Now I'm focused on manipulation.
Thanks. I think the introduction were already very interesting, so I'm excited to start with the actual questions and to hear all that you guys have to tell us. And I think in the spirit of the, well, actually, before starting, I just want to remind to everybody, if someone just joined, that please, if you have any questions, just add them to the chat. Or you can even put yourself on the box on the bottom right and then ask directly your questions. In the meanwhile, I was saying that I think the spirit of the workshop is that the idea behind the workshop is that there is a gap between how industry and academia are tackling robotic manipulation and manufacturing, and that the artificial intelligence and machine learning is playing an important role in this discrepancy. Therefore, I think it's important to start by defining what this gap is before actually trying to get into the possible solutions for this gap. So are academia and industry indeed really taking different paths, different approaches and solutions for robotic manipulations and manufacturing? And can we try to characterize what these differences are? Again, the question is open to all the speakers. And
I'm curious if it would be useful to distinguish between perception ML, has that transferred successfully, and the gap is more on RL for manipulation and control, or is it even a perceived gap on just using ML for perception? I'd be super interested to hear people's thoughts on that.
I mean, being the sort of learning skeptic in the group, I will happily say that we constantly use, ML-based tools for solving difficult vision perception problems, right? And so I think that has become just standard fare as an effective way to encode solutions to that particular class of, and I'm going to call them algebraic problems, right? Because they're one shot. Look at this and tell me what you see kinds of problems for the most part. And I think those, we certainly accept those as being very viable. I think we're still figuring out how to apply RL solutions at a level of trustworthiness and robustness to meet things that we're either able to do demos with or harder yet comfortable actually delivering to customers.
I would also go ahead, Matei, if you want to go first.
Go ahead.
Thanks. So I would also argue, for example, one of the things that I miss from going to actual conference is getting the swag from the conference. So this was from RSS 2017, and it was in Boston, and we were presenting DexNet 2 back then. So Jeff Muller was the main author at Berkeley, and we collaborated with them. I was one of the authors, and that is, for those of you that don't know, DexNet is applying deep learning for grasping. And actually, fast forward 5 years, there is today a startup from the same team of researchers out of Berkeley tackling that problem using DexNet in production, right? So it has transferred, it just takes time, right? It takes time to move from academia into a product that is robust enough that can add some value. And it requires a need, right, in the industry, right? It's not like the problem was not probably there 5 years ago. Now, due to the high demand on intralogistics, these kind of solutions make sense because there is no other methods that can cope with the variety that we see in an Amazon warehouse, for example. That being said, also obviously there is. I also make the case in my talk this morning that there are current approaches that also work very well, right? And so when we add something new into the mix, it's always important to see, okay, what are the conditions where this method performs better, and compared to something that is already used out there, right? To be fair with the state of the art, right? Because a lot of times when we, for example, in just being very specific on reinforcement learning, when we first started to popularizing it, right, there were a lot of articles saying, okay, this will really solve all the problems in the world, and that's not the case, right? It has a lot of limitations. It's obviously useful, but it has also limitations. So that's the last point. The last point that I want to make also is in terms of cost, right? And that goes to your question, Russ, in machine vision, a lot of times the cost of getting something wrong is not that huge, unless, of course, in autonomous cars you are missing a pedestrian and you hit it. I mean, obviously, but in terms of in manufacturing, I mean, the worst thing that can happen is inspection goes wrong, but it's a more mature field. While if you are manipulating, you can really mess up things, right? Particularly when you are inserting things or assembly, the price of getting that wrong, maybe a completely wrong product that can even explode or have deficiencies along the way. Your entire production line can be stopped because you mess up there. So it's not also a surprise for a lot of people that the first application that all this research is manifesting is with really suction cups, right? Because it's more forgiven, and really the fact that you are missing a picking is not a big problem, right? So these are just 3 thoughts on the topic. Back to you, Martin.
Yeah, and my point was going to be one of your 3, that it just takes time, right? That I strongly disagree with this assertion that academia and industry are looking at things in different ways, and there is this massive gap. We see huge success stories. They just take more time, right? Look at Fetch Robotics. It was acquired last week or the week before. A massive success story, a logistics warehousing robotics company, which was founded by people that used to be at Willow Garage that I worked with, terrific engineers. So what was Fetch their main technology? Autonomous navigation, so SLAM, in warehouses, in semi-structured environments. 10 years ago at Willow Garage, particle filter SLAM was considered kind of known in academia. People weren't really doing the research anymore because it was done. And the whole idea of, particle filter-based SLAM and, probabilistic robotics, when was ProbRob published? At that point in academia, it was already being studied for 10 years before that. So here we are, 20 years after maybe, the beginning of, probabilistic robotics becoming a big thing and particle filter SLAM becoming a big thing. And it took 20 years for Fetch to become acquired, to be acquired. Look at a torque-controlled robot arm, the KUKA lightweight arm. It was 10 years in development in academia, another 10 years, and DLR pushed it in as a research project for 10 years, another 10 years at KUKA. It took 20 years for it to become a successful commercial product. So in that sense, things like reinforcement learning used for motor control tasks. Sure, it's not translating yet. We're not seeing industrial products that use RL, Model 3 RL, for motor control. I'm positive that it will. It just needs more time. Russ, you were asking earlier, you're spending time, and people in your group are spending time thinking, why does it work? What's fundamentally different, and why does it work? And I've spent the last 5 years asking myself the same question, and I think I've come up with a satisfying answer, at least for me, and I'm confident there's something there. We're going to see it. It just needs more time.
And something I want to add too, and because we're talking about this in terms of maybe for manufacturing, is when we're looking at the areas where a machine learning solution can provide benefit, we need to think about kind of at what scale we want to utilize it. So if you want to make a certain solution more robust, it can persevere to local perturbations within an environment. That's something you can probably model as part of your manufacturing process, because kind of maybe what those limitations are going to be, or what the bounds are, and at least, train it or develop it to work within that scope. Whereas if you want it to be something that can more readily adhere to more global changes to a space. So this is the mom and pop shop that needs to change around their robot arm system for one manufacturing line versus another. That's a very different type of ask from a machine learning solution, but may be more of the value add to see it find its way into industry. And some of this what we see in some of the ARM Institute projects where they may be approaching it from getting one solution that can maybe transfer between multiple different types of robot systems or different applications, or just really operating within those robustness challenges for a particular application. And there's probably something there of, what does the industry actually want to see where robotics can add something that some of their traditional automation solutions don't currently have.
Okay, thanks. I think you all touched.
Maybe I'll just respond to Matej. So
go for it.
I mean, it's funny. Your example of the motor driver. That's a test for me, right? Like, do I believe that we're actually going to replace our motor controllers with RL? God, I hope not. I mean, what I would love for us to discover that like having some extra nonlinear terms in the low level could somehow do better or whatever. But if I have to every time I deploy a motor controller, I have to like run a million simulations, that's bad news. I mean, I hope that the process will be, maybe RL will open up our eyes to something, but then we learn something and there's like science happens and somehow we compress that understanding back down into like a very transferable, compact, doesn't require massive simulations in order to get a lot of the benefit, right? Because I think the cost, when we were talking about cost a minute ago, I wondered if you meant cost in terms of AWS bill, right? Because there's a cost there too, right? And I don't want the cost of my motor amplifiers to incur that cost, right?
I strongly agree that there are hopefully interesting things we can do, that it's not going to be just a policy that's just a fully connected MLP and then you just train it for enough steps and that's it. That there will be those nonlinear terms. Maybe there's going to be those nonlinear terms that will be trained as part of the policy, but will be inspired by our domain knowledge and by our knowledge of physics, and that would be fantastic. But it's this seductive. I think the well-known who wrote the famous manifesto about it's this seductive thing that scientists want their domain knowledge to matter, but ultimately the only thing that matters is just better search, better general search, and better general learning algorithms. I think, was it Rich Sutton, the famous manifesto? And to be honest, I've been running into that with the manipulation work, the in-hand finger gating thing that I mentioned today, and a lot of what we presented today is model-free RL. But that's not because we didn't try what we thought were clever things inspired by knowledge of grasp, mechanics. But ultimately, those didn't work. It was just, and there's something about also these reinforcement learning methods. The random exploration, I think, turns out to be incredibly powerful. Anytime you start biasing the random exploration based on your domain expertise and your domain knowledge, we have more often than not found it to be counterproductive. That just throws off the optimization. So much to my chagrin, a lot of what we tried to put in as domain expertise in grasping and manipulation ended up being counterproductive, and only with very light touches, model-free RL ended up doing the trick. At least in simulation, we'll see how it transfers. I agree with you that domain knowledge will matter, and we'll find ways to put it in, and it will make things much faster, much more efficient. It's not so easy, though. We have to find the right way to use that domain knowledge, and it's harder than at least I thought it would be.
But if Newton told you that here's your recipe, I've understood classical mechanics, you take a MLP that's this big and you fit it to your data, then where would we be today, right? I mean, there is something about levels of maturity of the field. I think what we're saying, I think RL is a great tool when our scientific understanding of the problem is not sufficient. It can help us explore those boundaries. But I would like to think that we will continue to compile our understanding into very general, practical things, right? That's just, as the field matures, right? I mean,
yes,
I agree.
Yeah.
I mean, yeah, you do you believe in systems science or not? It really becomes part of the question here, right? If you believe in systems engineering and systems science, then you want understandable blocks that you can actually interrogate and put together in novel ways to build more complex, more capable systems. And I think, RL, some of these deep learning techniques make it difficult to do that reliably. I mean, if I was going to complain about using the ML tools for solving some of the perception problems, is that every time we go tweak that perception problem a little bit, we have to go train, and training is not cheap. It's much cheaper to go systems engineer and put together really complex blocks that we understand the performance boundaries of to build bigger, newer systems.
And bringing the problem back to manufacturing, right? We have been producing millions of products with today's technology, right? Robots today, they last forever. They work very well in repetitive tasks where you have low mix, high volume. That's solved, right? So low mix, high volume, today's technology is perfect. Now you reduce the scope to, okay, what if I have a little bit more variability? There's still, computer vision works quite well. You can find ways to separate the parts so that your machine can find them easier, so you don't need to rely on deep learning. So the use case for where you really need flexibility is much more narrow than the entire field of manufacturing, right? So we also have to be conscious about that. There is definitely, as I said, a lot of advantages when things are not easy to model, like when contacts, as we have here alongside in all the presentations, right? The contact dynamics are super hard, but still there, the fact that you can explain something means a lot, right? When we think about manufacturing, explainability is usually one of the roadblocks that we'll avoid, even if the system is great. A technician should, right? These are the non-functional requirements of a system, right? A technician should, with very low, not necessarily a PhD in robotics, should go there and be able to fix something, right? If something is broken, right? Like my forklift hit my system and now I am 2 millimeters off. Can I calibrate it again or nothing works, right? This kind of use cases should be able to, should be addressable.
This is a very interesting conversation, and indeed, I just would like to go more in depth in some of the points. In a sense, I mean, for example, Matej is saying that in his opinion there is not such a huge gap, or because it takes time, right? And someone might think that the gap is there, but in both cases, I mean, even to reduce this time in order to get to what academia is producing, to get it into the industry, or to merge the gap, I mean, is it possible to define metrics, machine learning metrics, or evaluation methods, benchmarks, to really reduce this time that academia research can go into industry? I mean, is it even feasible to think to have some common benchmarks? And if yes, do you have any? And I was kind of impressed when before from said that, I mean, in his company they don't care really about the method they use, right? They have very specific criterion to decide if a method is successful or not, right? And whatever matches that criteria, then they are happy with that, right? Is it even possible to have something similar for both academia and research? Of course, in some sub areas of it.
Yeah, I think there's a lot of questions that come down to for evaluating ML that solutions that aren't in other solutions, like, do we need to start characterizing what the systems were trained on? You know, how much training they have, or to what fidelity of training, or you know, what data they've been trained on versus the data that they have been given, or the data objects that they've been given to grasp. You know, for some like algorithm testing, being able to characterize that element so you could actually do a comparison of one solution versus another and put them under the same amount of training into the same task set. I mean, even being able to quantify those elements is very, very tricky unless you're in a really, really bounded space where you're only a few dimensions. But all the problems we're talking about here are very, high dimensionality issues. So I think a lot of it starts there of knowing how to even quantify some elements of the solution, because otherwise there are existing manipulation benchmarks that are more focused on maybe singular portions of tasks, and maybe it's a matter of just inducing some variation into how those benchmarks are performed that would intentionally stress a machine learning or some other higher robust solution. At the moment, I'm not aware of any particular benchmarks that are specifically aimed at kind of flexing a machine learning solution versus another. But I think there are ways that we can tune some of our existing ones to match.
I mean, there's occasionally these grassroots efforts to start, to agree on the rules of the game, right? Of like whether it's rearrangement, or there was the DexNet, and Rob Platt and everybody were trying to put together something, and the challenge seems to always be that everybody wants to have a slightly different set of rules. Like some people want to go from only RGB. Someone says I want depth. There's nobody. Someone says I want a 2-finger gripper. Someone else says I want whatever. And I do feel like we have to. Well, it would be a natural evolution of the field to sort of agree on something and have everybody hammering on similar problems and sharing hardware. That would be awesome. And I keep feeling like we're getting close, but it hasn't quite happened yet.
I mean, from the point of view of the final goal, right? From I'm a manufacturer, will I adopt this technology or not? Metrics like number of successful picks, right? Doesn't matter, right? It matters the overall throughput of the system, right? So how do you achieve it? It matters the overall throughput with the ROI that I can afford, right? So how do I achieve it? I really don't care. And that's the difficulty, as you're mentioning, in this field, right? Because even the same problem of this Amazon challenge, right? It was solved in so many ways. Like Kindred solved it completely different than other approaches, right? So you can, I think fixing a set of grippers and robots and cameras will really reduce it will not reflect the heterogeneity that you see in manufacturing, where everything is absolutely different. At the same time that I say that, I think that more subjective benchmarks where, okay, you can compare two methods, but you cannot yet really say they are better from another. One may be cheaper than the other and achieve a slightly worse performance. But the moment that a sensor gets, some company finds a sensor that is cheaper, that solution will be better, something, right? So efforts like what NIST is doing with this assembly board, I think it has value, because at least there are some sense of, for some tasks like assembling wires or connectors, there is some learning to be made, but it's not as easy as say this method is better than this other, like you do in computer vision. All the details on what is your hardware, what are your limitations, in which conditions did you test it, this also matters.
I mean, there's also the matter of how much data do we need to collect to actually say that we have adequately benchmarked that solution. Achieving statistical significance when you're using static stimuli is already hard enough to do it in academia, because we've all read papers that have an N of 6 or whatever, and that's just, it is what it is. Where now, if we're talking about something that is intended to be robust and work in all of these various conditions, that number of test conditions and repetitions you need to do, obviously it skyrockets astronomically, which is why a lot of this, we do a lot in simulation, do a lot of training in simulation, a lot of testing in simulation, but being able to do that physically to validate, and not saying that necessarily needs to be as comprehensive as you would in simulation, but maybe there is some agreed upon minimum set, whether it's, bounding edge cases and something in the middle. I know some of the talks for today's workshop talked a little bit about that. Setting some defined criteria to say that the amount of testing we've done for this particular benchmark is sufficient. Finding where those are, that's a very big open question, but that we really do need to be doing some physical validation of any of this to really qualify it as being able to work in the real world.
That would be awesome, Adam. Yeah. I think it's really hard, right? Because the last product that I was working on when I was working at Siemens was flexible grasping on PLCs. Right? And how do you test it, right? Like the most difficult thing of my job was explaining the taxonomy of pin picking, because it's hard, right? Can your system pick up this object? I don't know, maybe, right? It's if I have seen it, yes. If it's something completely novel, maybe not, right? Until I try it, right? So there is a lot of trial and error. It would be great to find a set of objects and conditions that are representative for everything that is out there. I don't know if it's feasible.
You may be able to find minimum agreed upon sets for 80% of, I'm going to add more and more qualifiers to further narrow it down. But it's the same thing with the YCB object set. As widely used as it is your kind of base level set of objects for if you're working in the kitchen, if you're working whatever all the different kind of subgroups are. But it is something that is now very widely propagated throughout the world, used in, I'm sure all of our labs probably have a set of YCB objects. If not, we can provide you one from the Nerve Center. Similar types of object sets for, maybe more narrow manufacturing applications or whatever the application is, whether it's gathering different manufacturing widgets. Obviously this becomes a really, really difficult thing to bound because for manufacturing, it can span so many different areas. But certainly things like the YCB set, they probably don't currently cover a lot of those the kind of nuances with some of those objects, and in particular don't cover really anything yet with using objects to perform a task. We're talking about like insertions and screwing and things like that, where things like the NIST task board start to get us towards there, which is great. But you still have to do that kind of variation induction in order to really test an ML solution.
I don't know. Go ahead.
So I was just going to say, I think, all of those standardized test sets are great and obviously help unify how people understand capability of these various different approaches. But, the ultimate adoption with actual users is only going to happen when you can actually do meaningful proof of concepts and demonstrations, in their facility with their parts. And that's always going to happen. And those people, especially when it comes to doing, business critical manipulation or any robot deployment, they're going to be conservative. And so it's going to take a while for these technologies to move out.
I think that's a great point. And on the benchmarks and the standardized object sets, I kind of honestly tend to take the opposite view these days, in that I'm no longer such a believer. The YCB is fantastic. We have one. I think it was a great effort. I have yet to see a paper that uses the YCB as it was intended, namely by showing their results on the entire set, or at least on some logically coherent subset of the YCB. Everybody, or maybe I've seen the wrong papers, people will select arbitrarily 6 to 10 to 15 objects out of the YCB and show 90% success on them, And how were those selected? Well, it was the set that their method works 90% of the time on. And everybody does that, right? And that defeats the purpose. And there was a question earlier, and then given that we don't really benchmark, and it's very hard, how does industry know when technology is ready? And I think this goes back to Al's point. Ultimately, the only thing that matters is, are you saving somebody money? Are you alleviating somebody's pain point? And they don't know. They won't know when technology is ready for that, because they don't even know to look for this technology. They don't care what the technology is. They couldn't care less what the technology is. They just want their pain point alleviated. And I think what happens is that the gap gets bridged when somebody who knows the technology goes looking for applications and goes looking for domains where people don't even know that they need something, or aren't looking at robotics, right? So a roboticist goes looking at domains and eventually finds a domain where the technology is useful and does the additional systems work and engineering work, and then it gets deployed. And the only metric benchmark that matters is you're saving somebody money.
A good example are, for example, these recycling robots, right? These are a great example where ML is already making a big difference. You get the peak bron, nothing happens, right? It's much better than today's systems. Things are easy to detect. If you break them, they're already broken. So perfect use case for technology, right? The other case is what happened with this Pepper robot, right? The humanoid robot from your previous mother company, Al, that they build the company before the the application, right? So it's this kind of build it and they will come. I don't think it works in robotics. You need an application first.
Yeah, I mean, the Pepper story is actually much more complicated than you might imagine. But I think that's a really good point. We've been lucky, right? We were able to spend all this time doing basically research on legged locomotion and develop very significant public awareness of what we did and sort of interest in what we were doing. And for us to commercialize has been an interesting experience, because we do have some customers who just want a Boston Dynamics robot, and they don't actually care yet whether it's actually productive for them. And so we get our foot in the door with a lot of potential customers very easily, but that only gets you so far. And you have to then actually show them that it really does work and penetrate to the operations part of their organization, and not just the innovators, researchers. And so, I think this is really hard.
Maybe just to conclude the topic on the metrics and so on, we can use also the question that are on the chat from Megan and Jeremy, that they were asking how is industry supposed to know when the technology is ready for integration? And the follow-up is how is industry supposed to know which technology in a field of competing technologies they should be pushing for integration?
Well, to the point of Al and Mate, I don't think this really matters, right? It's not like you have a screwdriver and you're looking for screws, right? Or a nail, you have a hammer and you're looking for nails. You have a problem and you will look for the best solution to solve it, right? Now, related a little bit to that, what probably as an industry we can do better is not just do these cool videos that work 1 out of 10 and post it out there and see that it seems that it works every time, but be very honest also with the capabilities of the technology. TRL3 is nice, right? It works, but then there is this valley of death, 3 to 7, where institutes like ARM are doing a very good job on maturing this technology and at least showing that this works in a representative environment. That brings you to 7. This 7 to 9 is also another huge step that you need to climb, like huge. right? So making a product is super hard. I have a lot of respect of people doing products in robotics. I'm now wearing that hat, and it's super complicated, right? It's really, really, really hard to do a product in robotics. And at the end, you will use what probably if you have in this journey, you will have thrown 90% of the features, and you just have the only one that really matters for the customer, and that's what you go with, right? Even going back, right?
Oh, sorry. I was just going to say that you can think about the metrics that matter at each kind of TRL bound, right? So from TRL 1 to 3, all of the metrics you're going to care about are going to be really nitty gritty. Where these are like the things that you would measure as part of in an academic lab, someone who's doing their graduate work. They care about how accurate their vision labeling algorithm was, or whatever it is, blah blah blah. Then as you get to 3 to 7, now you're starting to apply this more as part of a task or process of what does that underlying capability actually get you? Because now you care about the environment, you care about where the information comes from, where it goes to. And then as you get into 7 to 9, as you're just alluding to, Juan, now it's ultimately going to be like cost, savings. It's probably some push and pull between there that are all sitting on top of all of your previous metrics, but it doesn't matter when you get there, right? So even for when we're talking about benchmarking or metrics as they go across those levels, they're going to be different along the way. So if we have methods that can span that scale, but with just different metrics that you care about at each phase, that would at least separate, what academics are going to care about while they're developing it, because they know that it's going to go into the realm that industry will care about it down the line. But we do have to have kind of a clear set of each of those.
I've almost said this from the last 5 speakers, but you say academics care about. And I feel like there is a fundamental problem here, which I think is a disconnect between academia and industry.
I cannot hear you, Russ.
Is that right?
I can hear Russ.
Yeah.
Okay.
Sorry, then it's just my end.
So, academics are not rewarded right now in any way. I mean, what would the normal incentive structure to have a benchmark or to go against those metrics? It would be like if it helped you get your papers published, or if it helped you get funding or whatever. But in any of those mechanisms right now, people are more rewarded to pick the 5 YCB objects that it works, or show some object that it didn't exist before. And that's going to end to put the one-time YouTube video on. I don't know if it's like science is broken totally, or if it's just like we're in that phase of our development for robotics right now. But I would say right now there is a big disconnect between what people are rewarded for in academia and what we're talking about throughout this conversation.
And I would argue that that's kind of fine, right? In academia, right? That's our role in the ecosystem to come up with ideas that might really have an impact 5 years down the line, or 10 years down the line, or 20 years down the line. If for things that can be commercialized by the end of next year, industry is way better set up than us. They don't have to, they have all their time to spend on it. They don't have to write grants, they don't have to write papers, they don't teach, they have big teams, they can build things faster. And that's what they're set up to do, and they're doing it really, really well. And we have our role to come up with ideas that are going to make a difference further down the line. And I think, the system works. It's, of course, and there are exceptions. Of course, there will always be, academics who come up with things that immediately have an impact. And there will be people in industry who do come up with amazing ideas that last for decades. But by and large, I think it's fine that we have our eye set a decade in the future.
Yeah, the danger nowadays comes mainly of the New York Times of the world, the Wire of the world, TechCrunch of the world, that will take a paper and completely exaggerates, and then they do an interview, and it's like, yes, of course, this will solve all your problems. It works in my video, right? So, but being realistic and ground that, maybe train more the public, right, on, hey, this robot that you see dancing is probably not using AI, right? It's not going to kill you. I mean, you know, it's good old-fashioned control that works very well, that takes a lot of time to tune. So doing that training and that kind of massaging our messages, I think, will help towards that, in my opinion, right? A lot of times our claims are exaggerated when it comes to robotics because it's so inside our brain, when we say so connected to science fiction, that we make a lot of assumptions in the near term, completely over-exaggerated. Well, and completely, this famous phrase on we completely underestimate the long term, right, but overestimate the short term. I think that's happening for most of the robotic research.
I mean, I think it's a deep question. There are other fields that have moved fast, broken. I mean, computer vision is benchmark driven, right? You can't publish a paper in computer vision unless you compare against other benchmarks, and that field has done pretty well, I would say, right? So somehow robotics hasn't made that change, or it hasn't chosen that path. I agree with you that we need to be able to do big sky things, but I don't know. I mean, I'm fundamentally torn. Are we, like, we don't cite each other's papers, we don't read anything that was published, 4 years ago or whatever. Is that good? Like, we need to be able to explore quickly, or is it, are we really just doing such bad science that we could be doing the same aggressive thinking, but be a little bit better as scientists? I actually don't know.
Is it a matter of more intelligently identifying the gap that should be filled, right? So, I mean, you can make a better solution to modeling, contact modeling. I know that was something that was mentioned earlier, but, do you need to back up and ask the question, is this the gap that needs to be filled in order to have the impact at the industrial level? Because some of it, this is a totally different field, but in the response robot domain, all the controller interfaces for teleoperated robots, pardon my French, but they suck. And they've sucked for so many years. But at the same time, all of the academic researchers in like RoboCup Rescue, they're working on these really newfangled, crazy AI-driven, solutions that, as far as I can tell, are not going to see the light of day into that field in a very long time, because we still can't get basic obstacle avoidance for a two-dimensionally driven ground robot. Now, there may be like logistical reasons why some of that doesn't happen, but that huge gap is because are we not solving the right gap that would actually have an impact on the industry versus, maybe solving some other metric that, for whatever reason, has been noted as being important.
Adam, you guys just need to buy spots, but separate issue.
We're in line. Don't worry.
I think I can go but to the underlying point there, and to what Russ was saying, I'm probably not the most cutting edge researcher at Boston Dynamics, but a lot of the stuff that I'm working on and the people I work with are spending their time on is stuff that is, years from appearing in our products, right? We are, they're also touching things that are going to appear in the next 3 months or 6 months. But we spend a lot of time reading old papers and reminding people, like for doing this manipulation stuff, I spent the last month basically reminding people how to do impedance control and, remote center compliance for peg and hole problems, because nobody remembers how to do that stuff anymore. And if you can't have that as a primitive, I don't care how fancy your ML thing is that you put on top of it, you're going to struggle to perform tasks meaningfully, right? You need that primitive capability that is just a well-designed local controller. And so I think there is, I can argue that, science is broken or the robotics field is broken because of the incentives for the academics, and having been one, I've been a lot happier since I quit. I got off that treadmill and got on to, doing what I think is real work. And a lot of the real work is really focused on deciding which problem is actually important. And I think one of the luxuries that we had, especially when we were doing the contract work, was that, we had sponsors who cared about, who trusted us to tell them what was actually important to get to the type of demonstration they wanted to get to. And that let us really focus on moving the technology forward to the point where, 10, 12 years later, we can actually sell a walking robot that people want to use, or at least they think they want to use.
Mm-hmm.
I think manipulation, needs to follow a similar trajectory, but that's also my selfish Boston Dynamics interest that we will succeed at making manipulation just work.
I mean, talking about these long-term ideas that academia can provide and what is important and what is not important to research on, just to kind of inspire the community. I'd like to ask to each and all of you, what would be an impressive result that you would really like to see, that you think is missing, and you would be really impressed if you see, that robotic demo, that paper, whatever. So in other words, what could be a Mondshoot problem that we should try to achieve in robotic manipulation as a community overall?
I have my favorite picks, for sure. But I think for anything I pick, I could get a really clever, like we call them robot whisperers around here, that could program a state machine that would get it done pretty darn well with enough hours on the robot. Or we could get a one-time video of an RL search that discovered something. So I think asking only what would be the demonstration that we want, I think isn't enough, right? Somehow it has to be qualified by how generalizable that approach was, how many hours of simulation it took, or something like that needs to be added on to the question, I think, to make it well defined.
So a little anecdote. I forget how many years ago. It was probably 4 or 5 years ago. Raybert did a TED Talk, and it was the first time we showed a spot robot with an arm in public. And, the robot was going to go pick a Coke can up off of a table and bring it to him. Pepsi can, I'm sorry, this is Mark. No Coke, Pepsi. I think we spent almost a month of time, calendar time, with about 2 or 3 people working on that demo. And it took like 2 days to make the demo basically work. But to run through all of the reliability issues to get what was a 1-minute demo to work at a level that we were all comfortable putting it on a TED stage was pretty onerous. And I think we said, gee, until we can do this 100 times in a row without messing up somehow, we're not going to ship it. So yeah, the TRL level matters, and it's not the specific demo. It is the set of capabilities, features that make a demo possible that have to all hang together in a reliable way. I'm sad that the search and rescue sort of robotics field hasn't made more progress than it has in the last 10 years, because I think there is a relatively benign, or at least well-defined problem that involves, basic locomotion, mobility over some terrain, and some pretty rudimentary manipulation that we as a field should be able to deliver on.
Yeah, if I can add on to I think it was Russ's comment about, maybe a demonstration isn't enough. It's a matter of making, is it a matter of making people care about more than the single demonstration? I don't know how we do that, but at the end of a project, there's always some final demonstration where they show it work a couple times, and then you read the report and hope that they did 10, 20, 30 repetitions of it, or in X number of conditions. That's not the sexy part of it, but it is the more meaningful part. So I don't know if it's a matter of just getting people to ask the right questions to be for adoption or to be impressed or whatever it is, but it's somehow highlighting maybe more just the importance of that aspect as opposed to just demonstration.
Yeah, I always like to compare these demos like when you see a cowboy riding a bull, right? It's like, okay, this is the cowboy riding the bull, and then the beast is tame, kind of, right? But it's not, right? It will like at some point kick him out. But if you just take that 10 seconds or that minute, you just really see that like you're in control, but you are not, right? It's like we are kind of taming a process here. Is seen on the long tail, what are the limitations, making it work 24/7 for X amount of time, in the conditions that are meaningful, and that's the impactful thing, right? Is things that are meaningful. Well, I want to see really a peaking system that works reliably for every single thing that I throw in any single lighting condition with the same dexterity that a human, which is far from the same throughput. But that's not super far away. I want to see a self-driving car. I mean, that is all over the news. I want to be in one. I mean, not just read it, but be in one. I think that's something that seems still like a moonshot to me.
True. And yeah, I mean, this is more a comment than a question, but yeah, I mean, I also agree of this reliability, right? That we want to have these systems working 24/7, or having these. We'd like to have these things not working just for that demo, for the video, but reliably. But I think also that for how maybe academia is, that there is always this rush of submitting the new paper, having and publications and so on. That's exactly the part that nobody really wants to do in academia, right? I mean, and as I said, for having that simulation, they had to spend an additional extra month. And because they had a specific target, that was the showing the robot in the TED Talks, right? It was very important. But if there is no such a stimula, nobody's really gonna do it. Not nobody, but the average researcher, right? And probably this is a problem of the overall system.
I don't think it's a problem. It's just not our place in the ecosystem. We are in the marketplace of ideas. We are not well set up to do the reliability part, unless it's something intrinsic to the idea. Maybe there's something intrinsic to the algorithm that doesn't lend itself to repeatability. And then somebody else will come up with a better idea that there's nothing intrinsically wrong with it. But it's just not our place in the ecosystem to spend the time to do that. And it's fine. We are optimized for something else.
No, but we're supposed to be scientists, right? And so we're supposed to increase the knowledge base of the world, right? And somehow I think I want to be able to think about crazy things and try something and publish it if it was a crazy idea. But I also want to add to the knowledge base. I want to like continue to build a foundation of understanding, and I think that's where we're failing right now. I mean, I not everybody, but I think overall the quantity of papers that get published compared to the growth in the understanding of the field, I think is out of whack.
What we can do about that maybe is be better reviewers, right? You review a paper and you look at the validation that they have compared to the claims that they make, and we can all ask ourselves, does this set of experiments support the claims? And then if we find that their validation doesn't cover certain cases, we bring that up, and we do a better job of not letting through papers that don't properly validate their claims. But I don't think that is a specific, one-size-fits-all benchmark that all papers have to go through. It's on us to put in the time as reviewers to understand specifically to each paper what's the right way to validate the claims, and are they meeting the bar or not.
I mean, I would actually, we should sign up and do a longer conversation. I don't mean to take away from the manipulation thing, but I think that's a hard question too.
It's a very hard question. Back when I was an academic, I used to serve on the IJRR board, and man, that was a hard job. And just not fun. I mean, I think it served the community, but man, no reward and lots of suffering and lots of angry people. To the research question though, and one of the problems I have with the ML stuff is because the ML stuff is potentially very black boxy, it's very difficult to transition it or to know how much you have to mature it as an academic, right? To be an academic and have an idea about something that's provable, whatever, some traditional control thing that has, you know, known input-output behavior and known bounds on performance, you can transition that thing to industry, and industry can then progress it in a rational, logical way. We don't have that science for these trained systems, right? We don't know how to take something that one of you guys built in your lab and turn it into something that is more mature and more robust in a systematic way. We have to just go start from scratch, essentially. And so I think that's one of the weaknesses of the RL ML techniques.
There is also, like, if you take a look at the field of industrial automation, which I don't think we do a good job to teach it enough in the US, but if you go to countries like Germany, that's also core. This has evolved for a lot of years, right? There are a lot of standards around. There is not a similarity with industrial autonomy, right? We don't know what to test. We don't know. We don't have tools, really. It hasn't really evolved. Or I don't know if this is even a field, but it will be required if more and more data-driven approaches, AI, are moving into manufacturing.
I think that's a very good point.
And I would go back to the example of particle filters for SLAM, right? It's a probabilistic approach. As such, you can never have hard guarantees. You can have probabilistic guarantees, which arguably may or may not be useful. And ultimately, the only guarantee you have is that, look, it just works. It's a probabilistic approach. It worked all the previous 10,000 times. It's going to work this time as well. And right now, based on such a black box approach with no guarantees, people are building companies that are incredibly successful in the marketplace. So one person's black box is another person's probabilistic approach, which won't have proofs. It just works.
All right, with this, we are actually a little bit over time. I mean, we had many more questions to ask you guys, but the discussion has been so interesting just with these questions, and I really would like to thank you all. Some of you stayed here with us for so many hours, so I think we can give a round of applause to all the speakers in this panel session. I think it was very interesting, and I really want to thank you. And with this, I declare the panel session over, and I hand the talk to Megan, who is gonna just wrap up the workshop with the final comments.
Thank you.
Thanks.
All right, thank you guys so much for coming to the workshop today. I want to thank all of our speakers so much for all of their great talks and for also participating in the awesome panels. If you're interested, we are going to continue talking on the Slack that we made for people who are working on AI for manufacturing robotics, but your manipulation people are more than welcome to join as well. And also feel free to check out the website we created to start to get the community talking to each other with regards to AI for manufacturing. And then also the videos for all of the talks for this workshop will be posted sometime later this week on the website. So thank you all for coming. If you have any questions for any of the speakers, just feel free to email them or reach out on the Slack. We'll see you maybe next year, who knows? But thank you all.